Good morning, good evening, my dear J warriors. Welcome aboard. This is your Captain Shreyas, your physics master teacher on the Vedantu J English channel. And I hope you guys are all doing great. And let's continue with our road series for J mains and advanced. And today I have some amazing questions, obviously, with the concepts. We'll start off with the concepts, go to the application, see some previous year questions, again go to the concepts, apply it, and see some questions. So everything covered in today's lecture. We'll be doing Newton's laws, all the three laws, free body diagram, how to draw free body diagrams for different situations, how to solve problems of equilibrium and motion, including friction, as well as we'll see pulley problems, problems involving spring forces, weighing machine, pseudo force, non-inertial frame, all these concepts in today's lecture. Okay, so that's your road series, which is concepts plus questions and PYQs. And I am Shreyas, your physics master teacher, Harvard, and welcome aboard. Hello, Soumya. Hi, Tony. We'll be doing, work per energy, and then we'll go to circular motion, and then we'll go to center of mass and collisions, and then we'll go to rigid body, rotation, all of these topics, right? Will be going sequentially. Hello, Gauri. Hello, Deepak. And one thing I need from all of you is the promise that you will be attending all the classes regularly, on time, without fail, or else you will see that there will be a break in the road series. It's simple. I want, even if you can't attend the live classes, at least watch it recorded. I want your comments after every single video. Sir, this lecture done. Sir, this much is done. I have done this much practice, or whatever is your current status. Okay. Even if you feel that it's not up to the mark, it's okay. Put it up. It's not like everybody will be completing 100%. Maybe some will be at 70%, 80%, 60%, 50%. Slowly over time, over the next few months, you will be able to complete as much as possible, right? That is our target. But that just because you're not done 100% does not mean that you stay back and feel sad about it and curse yourself. You have to push. From that 50%, you'll move on to 60, 60 to 70, 70 to 80. That's how you have to progress. Okay, so quickly like the session, mark your attendance, and subscribe to the channel so that you do not miss any of these lecture series. Okay, let's begin with the class. Yep. Yes, I do know about Walter Lewin. I have seen most of his videos. Hello, Arlene, Jenny. Hello, Tirupati D. Hello, Shriyari. Good evening. Good evening. Good evening. Class 11 portions, as much as possible, we'll try to do as soon as possible because mechanics is the major part, and then parallelly, we are doing magnetism, electromagnetism, all those things. Okay. Cool. So, the first part of the chapter is all about the three different laws before we go on to the different types of forces. Now, these laws are purely experimental. They cannot be derived using some other laws or principles. They are purely observational experimental laws which Newton observed a couple of 100 years back. The first law is called as the law of inertia. The second law is when you relate the momentum with the forces, and that's how the calculation of force happens. And the third law is an action reaction law, is what you get. And the first law says that if there is an object which is at rest, it will stay in rest, and if it is in motion, it continues its straight line journey unless it is compelled to change its state by some kind of external force. This tendency to resist the change in the state of motion is basically called inertia. Simple words, imagine you are studying, you have got that mood, you don't like to be disturbed. Tell me honestly, right? Sometimes you get that mood. Suddenly you are able to solve many questions. You don't want to disturb your mind, and you are like, okay, let me just, go with the flow. Sometimes you are watching a nice movie or you are spending time with your friends. That time you don't want to study. You want to maintain your state. So same thing applies in physics also. So imagine there is some object, let's say there is a rock and it is at rest. It will stay at rest. There is no reason for it to move. So the reason for somebody to change its state is the force. Without an external unbalanced force, there is no reason, there is no incentive, there is no, I don't have any because, or there is no, uh, reason for me to move or change my state. Same way, even if an object is moving with a speed, if it has some velocity, it will continue its velocity. It will not change the direction nor the speed, nor will it increase the speed, nor will it decrease the speed, unless it is compelled to do so by some other force coming from outside. So if you see something going with a constant speed, that means all the forces are balanced on it. There is no unbalance left. You might be wondering, what is this concept of balance and unbalance? See, if I apply some force from here and some force from here, and they both are equal and opposite, they will cancel each other out. Such is called as a balanced force. Such a system is called as a balanced force system. But if I apply more force from this side and less force from this side, so there will be a net force, there is a net resultant which is caused on one side, that is said to be unbalanced. Just like in a tug of war, two teams are fighting. As long as they are applying same forces, they are balanced. But one team is stronger than the other team, it becomes an unbalance, and you will see one of them will lose, one of them will win. Is this concept of balanced and unbalanced very, very clear in your head? Yep. Yes. Ragul, we are laying the foundation for mains and advanced. Obviously, there are problem solving sessions, PYQ sessions, which you need to attend additional to this. Yep. I need to increase the volume. Is that so? Is the volume fine? Just check Rolex OP. Yep. So that is what this law states. Okay. I will just write down all those things right over here. When I say balanced, when I say balanced system, that means whatever forces might act, they will cancel out each other. So the net force is basically zero. So the net force, the net resultant is zero, because since they cancel out each other, they cancel out each other. Whereas when you talk about unbalanced, when you talk about unbalanced forces, one force is more, other force is less. Okay, think of it like that. Then again, one force is more, another force is less. So you will see that the net resultant force is zero, not zero. This causes a change in state. So there is a unbalanced component which is going to cause a change in state. Next important thing you should know is what is the meaning of external versus internal. Imagine this, imagine this, there is a Pandu, okay, who does not want to watch a movie, and there is a Champa who wants to watch this movie. So what Champa does is basically she drags Pandu for the movie. Pandu has no mood. Okay. Pandu has no mood to watch the movie. I think the movie was Barbie movie. So Champa wanted to watch that Barbie movie. Pandu wanted to watch some other movie. Okay. So because of which, Champa is holding Pandu's hand and she's dragging him over there. So the force with which Pandu is pulled by Champa or Champa is pulled by Pandu, this becomes something called as the internal force. This becomes something called as the internal force for the Pandu Champa system. This is my system. So you will see this concept of system like you have seen in thermodynamics, or you might see in different places in chemistry and physics. So I can choose my own system. The choice is yours. The choice is yours. So for this choice of system, the force between them is becoming internal. But at the same time, we all know gravity is pulling Champa down. Pandu is also being pulled by gravity, all right? And Earth is not a part of the system. So this becomes probably the external force. This becomes basically the external force. So what is within the system is internal. What is from outside is basically external. And only an external force can cause a change in the motion. Kind of makes sense also. Just imagine this. Imagine this. You are you are in a bus or on a trolley like thing. Okay. This is a trolley like thing. And imagine there is a Pandu over here. Imagine there is a Pandu over here. Even if the Pandu, even if the Pandu bends and pushes this particular trolley, do you think this trolley will move? Do you think this trolley will move over this surface? No, right? Why? Because whatever force he applies, via his hands and his legs, that is basically an internal force. That is basically an internal force. But imagine there is a champa over here. Imagine there is a champa over here and she kicks this particular trolley like this. Then that force which champa applies on this particular system, that is going to be an external force which can cause a change in the state of that system. That is what it means. Is that right? Avanishri, welcome aboard. We are just starting. Low sound, low sound, low sound. Is it? Is it fine now? Hello? Check. Hello? Is it fine? Okay. Okay. Great. Great. So this was the concept of balance, unbalance, and external forces. Lastly, we talk about inertia. Inertia can be explained by different ways. Like you might have heard about this famous experiment, like you pull a cardboard sheet beneath a coin very fast. So the coin has a tendency to maintain its position. So it stays there because you have taken it really fast. The friction between the coin and the paper or the sheet was not acting for sufficient time to pull that coin, so the coin stays and it falls into the or that glass. So that is basically inertia. So a lot of examples when a bus driver brakes the bus suddenly, everybody has a tendency to keep moving forward. Suddenly the bus driver applied brakes, so you will basically fall forward. And if the bus driver is in full josh, full mood, and he presses the accelerator, you had a tendency to stay at rest. So the moment the bus accelerates, you will fall behind because you wanted to stay behind. Your body, mass, wants to always do whatever it was doing before. Remember that. Okay? I hope this is absolutely clear. There is a very simple conceptual question on this. And let's see if you guys can figure this bit out. If I tell you, if I tell you, listen, there is a box and it is on a smooth floor. It is on a smooth floor. And listen, there are two forces acting on it, one from here and one from here. If this is F, this is also F, same magnitude but opposite direction. What do you think is the condition of the box? What do you think is the condition of the box? What do you think is the condition of the box in this particular scenario? The options are option A, it is moving towards the right. Option B, it is moving towards the left. Option C, it is at rest. And option D, you can't say. What do you think is the correct option for this particular question? What do you think is the condition of the box? And an ideas, it will be there next week. Yep. Many of you might say it is at rest. Some are saying it is at rest. Guys, that is what most of the students say, and that is not the correct answer. The correct answer is can't say, because if you notice these two forces, the forces cancel out each other. So hence the net force is zero. So as per the first Newton's law of motion, the body, or basically the box maintains its state, maintains its state. Now, what was the state? It could be at rest or it could be in motion. Now, is that given to you? Is that given to you whether the box was at rest? No. Was the box moving? I don't know. So, if by chance this box was already moving at 5 meters per second, it will continue its journey with 5 meters per second even though the forces are acting. Those forces cancel. They can't accelerate or decelerate the body. Understand? Because they are cancelling. So it will continue moving towards the right. If it was already moving towards the left, it will continue doing its motion towards the left. If it was at rest, it will stay at rest. So hence the answer is I do not know, because not enough information has been provided in the question. Got it? Understood? No, it's not about friction, Sherlyn. It's not about friction. It's about insufficient information. It's about insufficient information in the question. It's a very simple conceptual question to explain first law. Now let's go to the second law of motion. Before going to the second law, we define this concept of momentum. Momentum is nothing but a vector quantity, which is the effect of mass and velocity together. So if I have a mass like so, and it has some velocity like this, then the momentum of that particular body is in the same direction. The momentum is in the same direction. The symbol is p, and that momentum is just given by the mass times the velocity. This particular momentum, it is a vector quantity in the direction of the velocity, and the SI unit of momentum, you can see this is kg, and velocity is nothing but meter per second, right? That is the SI unit of momentum, as simple as that, right? So now that we know what momentum is, which is mass into just velocity, we can define the second law. We can see what the second law is. The rate of change of momentum of an object is equal to the next external force acting on it. So actually, the correct word should not be is equal to, is this should be proportional to. This should be actually proportional to. Correct word is proportional. Is proportional proportional to the net external force acting on it. So let's see what it exactly means by this. The rate of change of momentum of an object is proportional to the net external force. Now, when I say net external force, that means imagine a situation where there are forces, but they do not cancel each other. If they cancel, I know it will continue doing whatever it is, but if they don't, then there is a net external force, which is F1 plus F2, like that. Many forces will be acting on the body. So this is the net unbalance. This is net unbalanced force. And what is it doing? It is causing a change in the state. It is causing change in the state of the motion, And this particular thing, which is the rate of change of momentum, rate of change of anything is nothing but the derivative, is nothing but the derivative. Rate of change of anything is nothing but the derivative of whatever thing you are calculating with respect to time. So here it is derivative of momentum. It is nothing but the derivative of momentum with respect to time, which means it should be dp by dt, which means it should be nothing but dp by dt. So this is proportional to this. So I can just write it down over here. dp by dt, this is proportional to the net external force on it. Now, I don't like that proportionality symbol. I will just write it as equality. I will just write it as some constant into dp bar by dt. In the next step, momentum is nothing but mass into velocity. So I can use the product rule. I can use the product rule of derivatives, and I can write it as m into dv by dt plus v into dm by dt. That is what I can write it down as. But usually, the systems that we study in our JEE syllabus are constant mass system. So whenever constant mass system is there, you will see this term will just become zero, rate of change of mass with time. But if the mass is changing, like a rocket moving up, then the mass will change. Then you will have this v dm by dt term. Or imagine a bike is being driven really fast, the petrol is being consumed, so mass will decrease. Or maybe you are running and you are drinking some water which is kept on the way. That is changing mass system, right? So all these are variable mass system, but most of the times a block is going, a car is going, the petrol consumption rate will be so less that you will generally ignore any kind of changes in the mass. So usually this second term is zero. Hence, our equation will end up being, hence our equation will end up being net force is equal to K times m into dv by dt. But what is dv by dt, guys? It is nothing but acceleration. Now, once we get till here, what we do is we define the unit of force. We say that if a mass of 1 kg is accelerated by 1 meter per second square, then the force acting on it is basically 1 Newton. So 1 is equal to 1 into 1. That means the value of K that you have over here should be 1 unit. That's it, without actually any unit, because kg meter per second square is actually a Newton. So K is a dimensionless constant with a value of 1. So in the SI system, you will see that this particular law will just end up being net force is nothing but mass into acceleration. So that is your Newton's second law in simple form for non-variable mass, for basically constant mass. If the mass is not constant, this term will be there. Okay. And if you do not use SI system, some weird system, some Pandu Champa system, then the value of K might be 3, 5, 10, 100, anything. So in SI system, this is true. So when somebody asks you what is Newton's second law, remember this is not the Newton's second law. Newton's second law is actually this. When you simplify it and do this, you get it. Okay. And a lot of people also claim this is the derivation of Newton's second law. That is even more stupid. How can you derive second law? Second law was this. So what is the derivation for this? Nothing. It is an experimentally observed fact. Okay. That's it. After this, whatever you get, this is a derivation of force is equal to mass into acceleration. Is that okay, everyone? Yeah. What is the correct method to write the Newton's second law in terms of cause and effect? Yes. So the correct way to write it down is basically something like this. Force is always the cause of the motion change of state. Then acceleration is the effect of it. Acceleration is the effect of it. Mass is nothing but how much inertia it has. More mass means it has more inertia. So that's the way you can write it. Without force, there won't be any effect. You cannot say, sir, this body began to move magically, sir. Sir, please apply force. Apply force, sir. The body is in motion. No, no. A body won't move just chumma and then say, hey, please apply force on me. It's not going to happen. It's not going to happen. Only when you apply force, then only there will be some acceleration. And that acceleration produced depends on how much inertia it has. If it has more mass, less acceleration. If it has less mass, more acceleration. That's it. Is that okay, Gauri? Absolutely clear on this front. Shall we go ahead? Everyone, smash the like button, mark your attendance already. Very good. Keep it up. Moving on now to the next thing. Just before we go ahead, simple concept checking question. Just imagine I tell you that the position vector is nothing but 2t I cap minus t cube j cap plus 4t square k cap. The mass of the body is 2 kg. Can you find the force acting on it? Okay, very straightforward question. You have to find the force acting on it. What we can do is to find the force, I need to find mass into acceleration. I know the position. From the position, I can find the velocity, which is the derivative of the position. So derivative of this will be 2 I cap minus 3t square j cap plus 4 into 2 is 8 t k cap. That is what the velocity will be. Take the derivative of this, you will get acceleration. Acceleration is the derivative of velocity with respect to time. Therefore, derivative of 2 I cap is 0. So 0 I cap because constant minus 3 2s are 6. So 6t j cap and 8t's derivative is basically 8. So 8 k cap. So therefore, the acceleration will be minus 60 j cap plus 8 k cap. Now, once I know the acceleration, I can find the force totally acting on it. So it will be mass into acceleration. That means 2 into minus 60 j cap plus 8 k cap. If you want, you can write it as minus 12t j cap plus 16 k cap newtons. So that is the net force acting on it. That is the net force acting on it. Tirupati, is that so? My voice is less. What has happened? What is wrong? Hello, 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 hello. Just check. It's clear. Without the headphone, it's not clear, is it? Let me do one thing. Let me use two mics then. Now, hopefully, it is better. Okay. Moving on now to the third law. It's all about action and reaction. So it says that whenever you apply a force, there is an equal amount of force on the first body. If one of them you categorize as action, the other one will be called as a reaction, number one. These forces are equal and opposite, yet they don't cancel out because they are not on the same body. That is what basically the third law of motion says. Now, it's okay to memorize it this way that, okay, one is action, one is reaction, they are equal, they are opposite, they act on different bodies, yet they don't cancel. So, all these things are very interesting. But let me take an example to make you really understand the Newton's third law of motion. Just imagine this. Just imagine this. Pandu wants to watch Oppenheimer. Champa, Champa wants to watch Barbie movie. There is a big conflict of interest. Pandu is dragging Champa to another screen. Champa is dragging Pandu to another screen where Barbie movie is there. Pandu wants to watch Oppenheimer. Okay. Now, in this situation, if both are pulling each other, let's say Champa is very powerful. Pandu did not eat only, full sleepy only, one lazy fellow he is. Champa, very powerful person. So Champa is pulling Pandu and Pandu loses the game and Champa pulls Pandu and takes him towards the Barbie movie. In this situation, who applied more force on the other? Did Pandu apply more force on Champa or Champa applied more force on Pandu? Come on, think and tell me. Yes, Soumya. The second law is consistent with the first law, like you can imagine it to be. It should be. If you put net force as 0, A is 0, that shows that second law is still obeying the first law. Got it? It's not like it's anything different. The second law tells me the calculation of the force. The first law tells me the idea of inertia and the concept of balanced, unbalanced forces and the concept of state of motion. Although it might sometimes feel that, why do I need the first law? But they tell different things. Okay. Champa applied more force on Pandu. Sakti saying the otherwise, Pandu applied more force. It looks like Pandu has more mass, I know, Sherlin, but still, what do you think might happen? Harborine says equal force. The correct answer for this is given by Harborine. Yes, it's equal force. A lot of people get confused. In fact, I have seen many teachers also answer this wrong way. People think because Champa finally won and dragged Pandu, so Champa applied more force. That's definitely not correct. Newton's third law at play over here. If Champa applies a force of, let's say, example, 8 Newton on Pandu, then Pandu unknowingly, unwillingly, subconsciously is also applying 8 Newton force on Champa. The fun fact is that this blue one is acting on this yellow Champa. This pink one is acting on this orange Pandu. They are acting on two different bodies. They are not on the same body. Number one, they won't cancel. Please understand, it's way different from saying you have this Pandu and there is an 8 Newton force from here and there is another 8 Newton force from here. No, this is not what I'm saying. No, this is basically the same, on the same body forces are acting. No. Here, 8 Newton is on this point, this 8 Newton is on this champa. They are on two different bodies. So they can't cancel unless they are on the same body. Do you get that? Number one. Number two, how is it possible that Pandu applies more force, Champa applies less force, or Champa applies more and Pandu applies less? That will violate Newton's third law. They both are applying the same force on each other. Then you will be like, sir, how did Champa win over Pandu? I agree, Champa is more beautiful than Pandu and all of that. Couldn't hear me. What is happening, guys? Is my voice not there on your what? Maha, what is happening? Hello, hello, hello. Am I audible, 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 audible? Yes, no. Please tell me. Yeah, okay. So, some of you might say that, how is this possible? Guys, understand that they both will apply the same force. In spite of that, Champa is able to win only because you will see the word friction later on. There is more grip. She has better grip on the surface. That means more friction. That's why she won. That's why she won. Whereas this Pandu had less grip. This Pandu had less grip on the surface. Maybe his shoes had worn out, so he had less friction. So, in a tug of war, it is not the force which you apply on the opponent team which helps you. More than that, it's the friction also which plays a very important role. So, with good grip, you can win the tug of war. Is that now clear? Is that now clear, everybody? Yes. So this is a very good example of Newton's third law, how it acts on different bodies, yet it doesn't cancel. This is not the situation. In fact, each of them is applied on different bodies. Number two, they are equal, they are opposite, they are not canceling also. And it's not like just because Champa is winning, she has applied more force. No, she has applied the same force as Pandu has. It's just that Champa had better grip on her on the ground by her feet, because of which she is able to pull Pandu. Pandu was on a slippery surface, or his shoes were, wet, or maybe they had worn out. Maybe that's the reason for that. That's the interesting thing. Very, very interesting. All right. So now that you are through the third law, how about doing a question? But this is a J advanced question. I don't think we are scared of any J advanced questions. Yes, Lions? Are we scared? No. Let's try to do it. Because I feel it is a doable question, which was asked in 2023 SCQ. Velocity is given as a function of x, y. This x cap means I cap, y cap means j cap. If you want, you can rewrite this or rephrase this equation in terms of ijk. Alpha is a constant, y and x are variables because they are the coordinates. What is a force as a function of x and y? I prefer writing this in a much better form. So I will write velocity vector as alpha into y I cap. I'll open up the bracket. So alpha y I cap plus 2x or 2 alpha x y cap means j cap. That is what the velocity is. The same thing I've just rewritten in a known form or a much better looking form. Okay. Now I want to find the force. If I want to find the force, what do I need? I need the acceleration. Eventually, I'll multiply by the mass. You can see mass is there everywhere. So just the concept is to find the acceleration. Let's do it. So what is acceleration going to be? To find that acceleration, I think I need to be little bit careful. It is nothing but dv by dt for sure. But when I differentiate this and this separately, alpha is a constant, bring it outside. So I'll have dy by dt, and then I have I cap plus 2 alpha dx by dt, and then I have j cap. What is exactly dy by dt? Rate of change of y coordinate with time. That means it is the y velocity. And this dx by dt rate of change of x coordinate means it is the x velocity. And this is j cap. Now, if you observe carefully this equation, you will immediately pick this up that this particular thing over here, alpha y, is actually the x velocity. This 2 alpha x is actually the y velocity. So put the y velocity and the x velocity now. It's not that difficult. So Vy is 2 alpha x, is 2 alpha x. So this is I cap plus 2 alpha. What is Vx? Vx is alpha y, is basically alpha y j cap. All right, substituted that. So what do I get? I get 2 alpha square x I cap plus 2 alpha square y j cap. Amazing. That is your acceleration. So now immediately we can find the force. Force is mass into acceleration. So therefore the force will be mass and acceleration is 2 alpha square, which is common. And I can write x I cap plus y j cap. So I think it is exactly option number A. Is that right? Yes, it is option number A. I cap is x hat, j cap is y hat. No, it is not option C, it is option A. Nikhil, when I say that there is a xy coordinate system, imagine there is a particle going like this and it has some velocity. That velocity will have two components, right? X component, y component, and if it is in 3D, it will have z component. What is this x component actually? If you see, there is some x coordinate. This is the x coordinate. The rate at which the x coordinate changes, dx by dt, that only is your x velocity. Same way, I can say there will be some y coordinate. This is y coordinate. The rate at which the y coordinate changes, which is dy by dt, will be exactly your y velocity. Is that now clear? Y dx by dt is vx and dy by dt is vy. So that's why dy by dt, which is vy, I have taken this vy from here because this will be vx I cap plus vy j cap. So vy I took it, substituted here. Vx I took it and substituted it over here. Is that understood? Now, clear, Nikhil, everyone? Isn't it a beautiful question? It looked initially tricky, but if you see the concept, it's not very difficult. It's definitely doable with some basic foundation. All right, moving on now to different forces because that is what will be needed now. And then after the forces, we'll be seeing, free body diagram and all of that. Can we find the momentum and differentiate? Yes, Raghav, it's one and the same thing. Either you differentiate velocity and find acceleration, or you find momentum and then differentiate. One and the same thing. You will still get the same answer, of course. All right. Force. There are different kinds of forces in nature. And when we solve problems, you will be showing these forces acting on bodies. This is no longer 9th standard or 10th standard where just the force is given 100 Newton, mass is given 5 kg, find the acceleration. Wow, full marks, 2 marks you got. Very good. Or sometimes they give one force is acting 10 Newton, other force is acting 6 Newton. Both are opposite. Find the net force, find the acceleration. There's fun in that. That is laddu problems. In the questions that we'll be seeing henceforth, you will be seeing that it will be a system. There is a block which is kept on a block, or a block is tied to another block, or two blocks are hanging over a pulley, or somebody is pulling at an angle by some force using a thread, and there is some box which is being rubbed against the ground. So many systems will be there. And over there, forces are not given to you. You have to identify the forces in different situations. That diagram or that situation might be described. You have to say, oh, wait a minute, there will be friction. Okay, wait, there will be gravity. Wait, there will be spring force. Okay, wait, this thread will be pulling from here and here. Oh, this block will be pushing it from here in this direction. Oh, this forces will act in this way. these forces will cancel, these forces will not cancel, acceleration is in this direction. So you need that trick, or I would say the eye, to see all the forces in that system. You need to also identify what direction, what magnitude, and if they are internal and if they are external. So that talent slowly develops with practice. That talent slowly develops with practice. Now there are basically four fundamental forces. There are fundamental forces in nature. Basically, they are like most elementary, you can say. Elementary. Elementary, or basically basic forces. One is gravity. Second is your electromagnetic. Earlier, people thought electric force is different, magnetic force is different. Later on, Maxwell showed that actually electric and magnetic forces are interrelated to each other. So that's why they were combined as one. Next is weak weak nuclear forces, and then you have strong nuclear forces. Strong nuclear forces. I know many people will be like, sir, weak nuclear, strong nuclear, just write nuclear. No, sir, why weak and strong? Then you can say weak gravity, strong gravity, medium gravity, very, very strong gravity. Sir, I will get more type. No, it looks confusing, but actually they are having a different formula, different theory. Just like gravitational force is way different from electromagnetic force. Just the names look as if they are associated with nuclear, so we could combine it in one. No, you can't, because their formulas, their structure, everything, the theory, hypothesis, everything is different. But these are the four fundamental forces in nature. In JE physics, basically you study this and this. This is not in our syllabus. Although you study slightly a bit of this weak nuclear force in the last few chapters called as nucleus, but that is also very, very basic. One paragraph will be there, that's all, not more than that. But mainly you play with these two forces in J, be it mains or even advanced. Okay. Now, once you categorize, or once you say that these are the four fundamental forces, any other force is a combination of one or more of these forces. So then you have basically your derived forces. When you have your derived forces, example, weight, or reaction force, or basically contact force, frictional force, or spring force, or the tension force, or the buoyant force, etc. All these are derived forces because they come from a combination of one or two or more things, or you manifest these forces into one of these. You look at it as one of these derived forces. That is the meaning of derived. Usually, you don't use these pure forces, at least in 11th standard. Very rarely you'll use it, except for the chapter of gravitation. Mainly, you are going to stick around with the derived concepts only. Okay, so we'll come to that. Also, you need to know one more thing, that as you climb up the ladder over here, these forces become weak. This is the weakest of all the forces if you compare for the same distance and similar objects. This is the strongest. This is the strongest of all. This is the strongest of all as you go down. Whereas if you go range wise, this one has a very long range, the gravitational force, Earth and Moon. But electric force can't apply between Earth and Moon. So these are basically very, very short range forces as you go down. So this is very short range. This is slightly better range, but still within the nucleus. This gets slightly better, few nanometers here and there, micrometers. This is in kilometers and kilometers, very, very long range. But this is very weak. This is very strong. So it just exactly how nature balances things. Gravity, imagine if it was also long range and also the strongest. And imagine this was very weak and also short range. No, nature balanced it out. If you are strong, fine, you will not have too much of range. If you are weak, no problem, then I will give you a very long range. So nature has automatically balanced these forces. Okay, till this point everything clear? शुभ, मेरे को बहुत अच्छे से हिंदी आती है, बट ये इंग्लिश चैनल है तो इसलिए हम इंग्लिश में बात करेंगे। ऑलरेडी आपके पास बहुत सारे हिंदी चैनल है, इंग्लिश में पढ़ाने के लिए कोई नहीं है, तो बाकी बच्चों का क्या होगा, है ना? तो इसलिए मेरा भी रिस्पॉन्सिबिलिटी हो गया। गॉट इट शुभ? All right. So let's start seeing all these forces one by one. Okay. All right. So these are just some examples. Friction, normal, spring, electromagnetic force, gravitational force, magnetic force, all these are some examples. So let's start seeing some common forces which we'll be encountering. Now, gravitational force is always attractive in nature. This is always attractive in nature, and it always acts between the two masses, acts between any pair of masses, any pair of masses. It can never be repulsive, and the force of gravity between any two objects is g m1 m2, mass 1 mass 2, divided by r square. This is universal gravitational constant, which is 6.67 into 10 to the power minus 11 Newton meter square per kg square, SI unit. This is the gravitational force. As you decrease the distance, the denominator decreases, the ratio increases, the force becomes strong. As you go far away, the denominator increases and the ratio goes down, the force reduces. So bringing them closer, force will grow. Taking them apart, the force will become weak and weak. They are very far. That's how the gravitational force acts. But, where is it? Yeah. But the same thing, when I usually call the weight of an object, when I usually call as the weight of an object, imagine there is some box, body, object, particle, person, whatever of some mass. Then there will be some gravitational force. Just one second. There will be some gravitational force acting on that mass, and this gravitational force acting on that mass is basically called as the weight of the object, and gravitational force is nothing but mass multiplied by the acceleration. The mass of the body is m, the acceleration is acceleration due to gravity. So you will see that the weight is equal to mg. This weight is nothing but the gravitational force acting on the body. Very, very important. So weight is the gravitational force on a mass due to the planet, due to the planet on which it is placed. Interesting thing, near the surface, G is almost the same everywhere. So it is roughly the constant anywhere on the surface of the earth. Very minor variations are there, which we are okay with. Even if you take it up a little bit, not much will change. Only when you take it hundreds of kilometers, then the value of G changes. Otherwise, weight is roughly the same here and there or up and down, because G variations are negligible most of the times. It always acts towards the center of the planet, towards the center of that particular planet, or basically vertically down, or basically vertically downwards. Vertically downwards. Obviously, the SI unit, will be Newton. And just to give you an example over here, imagine the mass of a person, is 5 kg, then the weight of the person will be 5 multiplied by g, which means 5 into 10, usual value of acceleration, so which is nothing but 50 Newton. So weight is 50 Newton, but mass is 5 kg. Now that's the thing with English and physics. When you usually ask somebody's weight in English, you ask Pandu, what is your weight? Pandu says my weight is 50 kg. This is in English. But in physics, when you ask Pandu his weight, he should not say 50 kg. Actually, it should be 50 into g, which means 50 multiplied by 10. So it is actually 500 Newton. So Pandu's weight will be 500 Newton. Understand that. Clear till this point? Yep. Also, remember one thing. Imagine you are on Earth versus you are on the moon. Okay, you are on the moon versus you are on the Earth versus you are floating in free space. You are floating in free space. In free space. In all these three scenarios, your mass is going to be the same. But m into g, which is the weight, this weight will be different because mass is always your inertia. It is nothing but amount of matter. How much are you made of? The same atoms, the same molecules. So your mass is going to be the same, but your weight will be different on different planets. In fact, in gravity-free space, it will be zero. Nothing, weightlessness, complete zero. Yes, Harboran, I will. Thank you so much. Is this clear, everyone, till this point? Great. So that was your gravitational force and weight. Now, let me actually bring this over here. You might have heard about this normal force and frictional force, right? Normal force and frictional force. Now, let me explain to you in a way which very few people actually know is the right way. Let me start off by something called as a contact force. Something called as a contact force. The name only tells what it means. It is in contact with something. Imagine there is a box like this. There is a box like this. It is in contact with my hand. Maybe I'm holding it at an angle. That's okay. There's some contact, hence there is a contact force. I throw this box up. It's no longer in contact. For that brief moment, there is no contact force. I am touching this screen. Yes, there is a contact force. I leave my hand. There is no contact force. I'm standing on the ground. Yes, there is contact force. I jump in the air. For that small moment, there is no contact force. Do you understand what contact force is? Whenever there is contact, there is a contact force. As simple as that. Now, imagine this. There is a box which is kept on a surface. Horizontal, vertical, slanting doesn't matter. If you zoom onto it, if you take a small portion of it and zoom onto it, you will see that none of the surfaces are regular. They will have some gaps, some cracks, some valleys, some peaks like this. And no matter how much you polish it, it will always be like this. Okay? It will always be like this. They might not perfectly match. It's some random thing. This is of the ground or the table. The yellow one is of the box. What you will see is at the molecular level, you will see that this table surface will apply electromagnetic repulsive forces when the molecules of the box come very close enough. So you will see some teeny mini electromagnetic forces here and there, 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 like this. You can see that. So these are teeny mini electromagnetic forces. The resultant of all these electromagnetic forces could be at an angle, could be at an angle. So maybe I'll show it like this. This is the resultant of all these teeny mini forces. At the same time, think about it, by Newton's third law, there must be an action reaction kind of a pair. So if this force is there, then there is a reaction for this also. If this is there, there is a reaction here also. So similarly, you will have reaction forces everywhere, guys. For every single force over here, there will be a reaction force everywhere. Everywhere you will see that there will be a reaction force, maybe like this, maybe like this, maybe like this, maybe like this, maybe here, maybe here. Okay, like this. I just shown it randomly. Okay, so all the reaction forces. If on one side on one side you call these as action, which is on the box by the table, you will see there will be a reaction by Newton's third law. This is the Newton's third law of motion. This is on the particular table surface. This is on the table surface. And the resultant of them, obviously, the resultant of them will be like this. Action, reaction. Is that clear? If this is action, this is basically reaction force. This is basically called as the contact force. What is this called? This exactly is called as contact force. This is called as a contact force. So at the end of the day, it is nothing but the electromagnetic forces between two surfaces in contact. Between two surfaces, basically in contact. Now, this contact force, which is there, I can split it up into two components. So, maybe, but first let me complete the PYQ session of current electricity capacitors. I have done one part. I think I have done April session. Let me do January session, and then over the week we'll do PYQ session of NLM also. Okay? Yep, definitely. Now, you will see, my dear students, that this contact force, this particular contact force, can be actually split into two components. Can be actually split into two components. One component is basically here, and other component is basically here. One is perpendicular, one is parallel to the surface. The one which is parallel to the surface is basically called as friction. The one which is perpendicular is called as norm. So it will be normal force plus friction force. So normal is the one which is always perpendicular to the surface, and friction is always the one which is parallel to the surface. They are just nothing but, at the end of the day, the components of contact force. They are nothing but the components of the contact force. Is that clear, everyone? Also, you will notice by Pythagoras, n square plus f square, the whole thing under the root will basically give you the magnitude of the contact force. Will basically give you the magnitude of the contact force. Clear? So that is why you will see most of the times, if there is a box kept, you will see the normal force will be shown perpendicular to the surface. Even in scenarios where there is a box kept on an inclined plane, you will see that the normal force will be shown again perpendicular to the surface. Imagine something is, pushed against the roof, the ceiling. This is nothing but the ceiling, and somebody is basically pushing this particular box against the ceiling. You will notice that there will be a normal force like this. There will be a normal force like this. Normal force is always directed away from the surface in which it is in contact with. Is that clear, everyone, till this point? Yes. Can we use pre-made notes like in Nurture series? Yeah, definitely, Nikhil. Why not? Definitely. Mind blowing. Very good, Harbour. Yes, Shubh. I hope I have answered your query. And by the way, Shubh, I'm called Captain, Capto, like Ninja Ma'am, Nabu Ma'am, Captain Shreyas. Yeah, that's my nickname. I think it's right over there. Next, friction. Every time there is a tendency to move or some motion which is happening on a rough surface, you will see that the friction always opposes the motion. We'll be talking about this in detail later on. For now, this diagram is enough. This understanding is okay because we'll be studying friction in detail after some time. Okay, so you pull something, the motion is being resisted because of the roughness. That friction acts always parallel to the surface of contact. That is your frictional force. Till now, this much is enough. Let's go next, which is tension. These two people are pulling a rope like a tug of war. Yeah. Arlina, Jenny, I think it will end at 8:30 around that time. Ashwath, I can take the classes after 6, but the problem is the lectures are so big that it will go beyond 9 o'clock, and we have our PYQ sessions at 9 o'clock. So we need to balance everything, right? There is only limited time. We can't start the PYQ at 10 because then you need to sleep also. So a lot of content being given on the class and the channel. So maybe whatever you miss, hopefully we'll be covering it up as a recorded lecture. Yep. Cool. Now these two people are pulling a rope. When you pull this rope, the molecules inside this rope, they tend to move away from each other, and there are bonds between these molecules which can't be broken because it is a solid. So those bonds which get stretched when you pull a rope or a string or a wire, those bonds tend to bring back those molecules back together. That force between these molecules is basically called tension. So if you hypothetically imagine any cross section of that particular rope, it will look probably like this. This is one side. This is not actually cut. It's just shown over here. All these molecules to these molecules will pull it like this, will pull it like this. And by Newton's third law, the same forces should act in the opposite direction on these molecules because the bonds are being stretched when you pull anything. So the collective force is basically called tension. Many times I hear people asking what is the direction of tension, and people say it is this way or that way. I'll tell you, if you take any point in the string, the tension actually acts both the ways. It depends which part of the string are you considering. If you are taking this end of the string, then on this side of the string, the tension will be this way. If you take this side of the string, then you will see that on this side, the tension is that way. So tension is actually both ways at any given point. It depends for that point, which side are you taking, this side or that side. But whatever you take, you will notice one simple thing, that tension always acts along the rope or the string, number one. You will never see tension acting at an angle. Okay, you will see tension always acts along the string, and also the tension force always acts away from the string that you have chosen, away from the string element that you have chosen. Look at that. This is the element that I have chosen. The tension is acting away from it. This is the element I have chosen. The tension at this point is away from it. So it always acts away from the element that you have chosen. Okay, okay, perfect. Another thing is that if by chance the value of tension, if it is zero, then it means the string or that rope is basically slack or basically loose. Meaning, imagine a string which is just lying down like this. There is no tendency to pull. The bonds are very happy, the molecules are very happy. There is no tension only in the string. Just like after your exam, the only tension is of the results, but otherwise there is no exam tension. Same way, guys, these molecules are at chill. They are chilling. They are lying down peacefully. Only when the tension is more than zero, that's when the string becomes taut. So you will hear this word very, very often, that if tension is more than zero, the string is said to be taut. TAUT, or basically it is under tension. I would say it is under tension. Very, very important. Is this absolutely clear, my dear students? Everyone till this point? The concept of tension. Does string have any weight? We'll be coming to that, Satya, on the next slide. When we try to calculate the tension, please bear this in mind. Usually, our strings are, are basically light or basically massless. These are basically our ideal strings. These are basically an ideal rope or basically a string in most of our problems. In such cases, what will happen is that you take any point on the string, whether here, 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 or here, the tension will be the same. In fact, it will never ever happen that tension on both sides are different. If here the tension is T, here also the tension is T, the tension throughout the string is the same. Throughout the string element is basically going to be the same. It will not be different. But if the tension, sorry, if the rope has some mass, if the rope has some mass, then you will notice that maybe here the tension is T1, maybe here the tension is T2, maybe here the tension is T3. Then in such case, tension may be different. The tension may be different, and this is the case when the rope has mass, when the rope has some kind of mass. That is what will happen. I'll give you a simple example. Just imagine there is a string which is hanging, and there is a box. There is a box of mass m over here. Imagine two different scenarios. First scenario, this is an first scenario, this is an ideal string. Second scenario, this is a rope with mass. This is a rope with some kind of mass. When it is an ideal string, what will happen is whether you take this point, this point, this point, or this point, doesn't matter. As long as you are considering some amount of string with that mass suspended, this part of the rope has no mass. This has no mass of it. So, when I show the forces of this part of the body, the only force will be the weight of the block. Weight of the block, which is nothing but mass into g. Because this is at rest, this must be balanced by some other force. Remember, this whole thing is just lying there, so it is at rest. So hence the forces must be balanced. There must be an equal and opposite force which will come from here, and that would be the tension. That's it. Hence, I will say tension will be mg everywhere. Everywhere on that particular string. This tension will act to balance the weight. This will act to balance the weight. Is that clear? Everywhere the tension is same. That is what we said also. Whenever you have massless string, the tension everywhere is same. Whatever is the value, it will be the same. But when you have the rope with mass, here comes the challenging part. If you take this much part of the string versus this much part of the string, you will see this has less mass of the string versus this has more mass of the string, which means when you calculate the forces on this particular part of the system, there will be some weight here, but this would be less weight as compared to this. This will be more weight. Do you guys agree? This will be less weight because of less mass. This will be more weight because of more mass. To balance it out. Why? Because everything is going to be at rest. So what you will see, there will be some tension over here. This tension will be less and this tension will be more. So that means as you go higher and higher, you will get more tension. You will get more tension in that rope. And as you go lower and lower because of lesser mass, you will get less tension over here. It kind of makes sense because this point has to only help this much mass. As you go up, it has to hold not only this mass but also this additional weight of the spring. That is why the tension increases to hold that much more mass. Is that clear? Yeah. Hello Supriya, long time no see. Hello Adiksha, hello Arohi. I hope you guys are doing great and looks like your college or school just got over. Till this point clear? Everyone give me a thumbs up. Shall we go ahead to the next concept? Did you understand how tension works? What is the meaning of tension? And tension in an ideal string versus a string which is non-ideal, which means it has some mass. Okay, all these are important pointers regarding the tension. Moving ahead to the concept of spring force. All right, let's move. Spring, I'm pretty sure everybody has seen in your life, in most of the pens, especially these, I have one, these kind of pens. These kind of pens, you open them up, you will see there is a beautiful, oops, I dropped it. Beautiful spring inside of it. I hope you can see it. There's a beautiful spring inside of it. And the spring, you can see that as you press, now this one is really teeny meeny. As you press, it will compress, and as you pull, it will elongate, but it will want to come back to its original shape and size. That's what will happen, correct? So don't worry, I didn't sacrifice the pen. I can get it back, and it's back in working. Yes, there you go. So this particular spring force arises because of the deformation produced, and you will see that the spring force is directly proportional to the deformation which is produced. If the deformation is x and the spring force is F, it is proportional to that, and I write it as K times of X, where this K is called as the spring constant. The unit of it is Newton per meter, and it depends on the material, shape and size of the spring. Here we'll not worry about how to calculate if the material is given aluminum, steel, tungsten, shape if it is different, if the size is different, diameter is different, number of turns if it changes. That part we are not worried about, but you should know it depends on the material and the geometrical characteristics of the spring. That is your spring constant K. It is given to you, or you will find it out if X and F is given to you. This force is the spring force, X is basically the deformation. Now what happens is, many people remember this as minus kx. I say don't remember it as minus kx. Just remember the magnitude is kx. Direction you can show automatically depending on the problem. It depends. And I'll tell you why. As long as you know it is k into x, that's more than enough. Just imagine this. This is a spring. Okay, this is a block over here. Now you elongate it. You elongate it like this. Now, if you consider the spring versus the block, you will notice since the block has gone here, the deformation of the spring is x. The spring will pull the block like this. So the force on the block will be in this direction, whereas you're pulling the spring or the block is pulling the spring away. So the force on the spring will be in this direction. So if you write force on the block, yes, vector wise, it is minus k x bar, because if x vector is shown, it is in this direction. Direction wise, this force is negative of x bar, whereas this force is going to be k times of x bar. So it depends whether it is negative or positive. It depends on which part of the body are you considering. Is it the spring or is it the block? My advice, you don't worry about it. You just show the direction, automatically you just put the magnitude, everything else is solved. So don't remember plus kx or minus kx. Just remember it depends, the direction depends on which body's forces are you showing, which body is under consideration. If it is spring, it's very natural. You are pulling the spring. Obviously, the force on the spring will be this way. This body will be pulled back by the spring, so it will be this way. It will be very, very obvious. Yep, correcto. Awesome, awesome, awesome. Now that you have understood it till here, just to give you a simple conceptual question. Imagine they tell you that there is a spring and there is a block of mass, let's say 15 kg, and their spring is having a constant of 300 Newton per meter. Question is, at equilibrium, how much will be the elongation? The question is, how much is the elongation when it is at a steady state? Steady state means it is stationary. How much is that elongation? So what I will do is, I'll just consider this body, which is that mass. If I just look at that mass, which is having a mass of 15 kilos, the forces acting on it are its own weight, which will be downwards, and that weight is mass, which is 15 into g. Apart from that, the spring will pull it up because remember, it will get elongated because of its own weight by some amount x. So the spring will pull it upwards. So there will be a spring force whose magnitude is k. K is nothing but 300 multiplied by x. Now, since it is in steady state, that means this particular body is at rest. And once you are at rest, that means all the forces basically cancel each other. The net force should be zero. Hence, I will just say the spring force cancels out the weight. The weight is nothing but 15g, and spring force is basically 300x. 15 goes with 300 20 times. So x will be, g is basically 10. So x will be nothing but 0.5 meter. Is that okay? 0.5 meter, which is nothing but 50 centimeters. Yes, this is nothing but 50 centimeters. So the elongation will be 50 centimeters. Is that clear, everyone? Anbu, center of mass collisions, moment of inertia will come next month only, not this month, because we are going to do next week. I think we'll do magnetism a little bit, and then we'll go to no. I think we'll do work power energy and circular motion, and then we'll go to magnetism. Yeah. Yeah, let's do work power energy because we'll need some energy related concepts and circular motion concepts for magnetism. So we'll do that first, and then we'll go to magnetism, and maybe then after that center of mass collisions, and then rotational motion. Okay, fair enough. Now what we have been doing all this while is actually showing the forces on a body, and that is what is needed for solving the questions. Whenever you get a question and you want to find out how much force is acting, what is the acceleration, what is the tension, how much is the friction, will it move or not, will it be moving this side or that side, when will it stop, where will it stop, and you are bothered about bothered about what forces are acting, how will it affect, what is the cause, what is the effect, then you will be drawing this FBD. The moment you hear this word FBD, meaning all you have to do is show the forces acting on the body. But before that, what you do is basically make a choice. I will say choose a system. Choose your own system. Now, please remember the choice of the system, the choice of the system will decide how long or easy the solution is to the problem, the solution to that particular question. So choose it wisely. Just because, oh, I am free to choose any system, I'll choose anything. No, it will depend what you are choosing. Accordingly, the length of the problem will change. So be very wise when you're doing that. Next, you will only show the forces on the system. On the system, when I say on the system, it basically means external forces only. And remember, obviously, completely ignore internal forces. Completely ignore internal forces. Very, very important. Lastly, always show the effect. Always show the effect. Now, when I say the effect, it basically means the acceleration. Show the acceleration, and if needed, make a choice of coordinate axis, coordinate axis, and resolve resolve the forces if needed. Usually we'll see sometimes if it is an inclined plane, you might take x-axis as the inclined plane perpendicular to the incline as y-axis. If everything is horizontal, you will take x-axis as horizontal. Things are inclined, your x and y coordinates will change. If things are vertical and horizontal, your x and y axis will be your regular x and y. So you can change it according to what that situation demands for. All right. So that choice is allowed. And accordingly, once you choose x and y, you will resolve fx, fy, ax, ay, and then you will use Newton's laws. This is the main concept of FBD. So let's see some questions on it and how do you basically draw the free body diagram. Let's start with a basic question. Imagine there is a Champa and she's standing on the ground. Imagine this is a Champa standing on the ground. I ask you, draw the free body diagram of Champa. Champa's mass is m. So I'm like, okay, fine, sir. I will draw the free body diagram of Champa, sir. Very, very simple, sir. So this is Champa, sir. The forces acting on Champa, the last Champa. What are the forces acting on you? Champa will be like, I'm being pulled down by Earth. So weight of Champa, which will be nothing but m into g. Fine. Apart from that, there will be a normal reaction on Champa on her feet over here. So there will be a normal reaction on the Champa. And everything is at rest. These are the only two forces. She's just standing over there. So I will say normal force is equal to mg. Normal force is being balanced by the weight force, which is nothing but mg. Fair enough. Now I ask you, she's standing on Earth, right? Okay. So how about showing the free body diagram of Earth as well? We'll come to that. We'll draw the free body diagram of Earth. But before drawing that free body diagram, I have an interesting question. If weight is considered as action, can you tell me what is the reaction or where is the reaction? Quickly in the chat box. Can you quickly think and tell me where is the reaction, my dear students? If weight is the action, can you quickly think and tell me where is the reaction? Yep. I'll be like, sir, if weight is the action, come on, think, think, think. I want the answers in the chat box right away, right now. It will be the normal, is it? That's what I was expecting. That is what most of you will say, but that is not correct. See, remember in Newton's third law, imagine there are two charges, proton, proton, positive, positive. This repels this proton. This in turn reacts and applies a reaction on this proton and repels it. If this is electric, this is also electric. Keep that in mind. If one is electric, the other one is also electric. They are of same kind. Number one. Number two, they are going to always coexist together and they are going to be in pairs. They are going to be pairs. Number three, they will never act on the same body. They will never act on the same body. So this normal is applied on Champa. Weight is also on Champa. How is it possible that this normal will be the reaction? Number two, weight is gravitational. Normal is the electromagnetic repulsive force between two surfaces. One is electromagnetic, one is gravitational. Can't be true. They are not pairs. They are two different things. Even if Champa jumps, weight will still be there. But since she has lost contact, normal will be absent. How is it that action is there and reaction has gone? When she jumps, where is the reaction then? So normal can't be the reaction. So that's why I said free body diagram of the earth. So what will happen is weight of Champa. Champa is pulled by the earth will be pulled by Champa like this. The weight will be pulled by Champa on the earth like this. So if this is action, the reaction is this one on the earth. On the earth. They will always coexist together, whether Champa jumps, does not jump, sleeping, whatever. Yes. Yes. Anime lover will be doing that towards the end. Number two, this normal is on Champa by the earth. So the reaction will be on the earth by Champa like this. So, my dear students, if this is considered as action, then this is reaction. If I consider this as action, this is reaction. It's up to you who you want to call action and who reaction. But this is a pair. This is another pair. Is that now absolutely clear and mind blown? Okay. So I'll repeat. Champa is being pulled by the earth. Champa has the moral obligation to pull the earth by the same force. So if earth applies W, which is mg force, on Champa, then earth will also be pulled by Champa with the same force. Undoubtedly. This is like m1, m2, mass 1, mass 2, g m1, m2 by r square. So that force acts on which body, m1 or m2? Both. It's a mutual gravitational attraction. So Champa and earth both get mutually attracted. The earth supports Champa. So earth is supporting Champa by applying a force up. Champa will push the earth down. So this is reaction. Is that clear now, Ashwath? Absolutely. And Arlena? Hello, Sony. This simple free body diagram teaches you so many things. So a lot of people try to solve very complicated questions and then you get stuck. Reason being concepts are not clear. That's why please clear the concepts in Newton's laws. See, the complexity of questions in Newton's laws is endless. Nobody can say I have solved all the models of questions of Newton's laws because every time there might be a new situation which might come in Newton's laws. So that will come via the practice, which we'll be doing as much as possible over the period of time. So guys, first understand every basic fundamental concept over here. Let's do this particular question. Draw the free body diagram of all the three blocks A, B, and C. Okay, let's do this. What are the different forces on these blocks? Let me show maybe A over here, then this is B maybe, and maybe this is C over here. Now, first things first, show all the regular forces. Show all the regular forces. The most common force is the weight. So first start as with the safe forces like weight, then go to the more complex forces like normal, then friction, if at all, then tension, etc. Yeah. So this session PDF uploaded in Telegram or Jungle Book, both places, Shriyari. I always upload it in both places, Telegram as well as Jungle Book. So for those students who are already on our Telegram, it is beneficial. Some students might be seeing this lecture maybe after a year, after 5 months or 4 months. Number two, they might not have access to Telegram, or maybe it is too difficult for you to scroll up and see it in the Telegram. That's why I arranged everything in the Jungle Book as well. So you have both the options. Okay, cool. Can we draw the FBD for circular motion? Yes, why not? You can draw the FBD for everything. FBD will come not just in circular motion, but also in work per energy, even in electromagnetism, EMI, magnetic forces of on current carrying wires. Everywhere you will see FBD, free body diagram. It's not restricted to this chapter. This is a general thing, like plus minus integration derivatives. You see it everywhere. So first of all, let's show the weight of this block, weight of this block, and weight of this block. So what are these weights going to be? They are going to be MA into G. This will be MB into G. This will be MC into G. Okay. Next, let's show normal. See, be careful over here. A and B are in contact over here. So there is a normal force between them over here. So A and B have a normal force between them. So A is being pushed by B, B is being pushed by A like this. Is that clear? Like this, what I'm showing. Again, A is being pushed like this by B. So B is also being pushed down by A. So if I call this as N1, this will be also N1. So N1 is the force of action reaction between A and B. Remember, A can't be pushed by the ground or C. That is illegal. It is not even in touch with that. It is only between the contact surfaces which are touching each other. Yeah, very good. Number two, on B, C will also apply a force because this is a contact surface. So you will see that there will be a normal force on B and the reaction will be on C. So I can call that or label that as N number 2, normal 2. Action, reaction between B and C, between B and C. Lastly, C is on the ground. So the ground will apply some kind of reaction and I can label that as N number 4, N4. That's it. That completes our free body diagram. If at all I had to write the equations, I would write it like this. N1 is up, MAG is below. So N1 is equal to MAG. Here, N2 is up, MBG is down, and so is N1. So they both will balance N2, plus N1. N1 is down, MBG is down. Together, they balance N2. But wait a minute, N1 is MAG. So it will be nothing but MBG plus MAG, which kind of makes sense that it should be the total weight, which is so the contact force between these two will be the total weight which is above it. The total weight will be supported by it. That's the value of N2. If you talk about, why did I put N4? I can call it N3 only. N3. Yeah. So here I can see N2 is down and so is MCG is down. That will be balanced by N3, but N2 is this one. So it will be MAG plus MBG plus MCG is basically N3. That means your N3 will be the total weight which is up. MA plus MB plus MC, the whole thing into G. That is what N3 would be. Is that right? Understood how we have drawn the free body diagram, considered the forces properly? Cool, clear. Shall we go ahead to the next one? Yep. Srihari, I will try, my dear student. Uh, just give, right now, what I'm doing is trying to do as many PYQ sessions along with the chapters which I've done in the road series. If I see that, I find some time somewhere, I will definitely do it. Right now, I have my regular classes in the paid platform also. Plus, I'm also on the NEET English channel. So I have to balance everything. And plus 11th standard students and 12th dropper students, everything basically 2025 and 2026. So a lot of things are there. So that's why we um, might be taking classes to balance everything properly. But rest assured, I'll try to do as much as possible in the next maximum September. You know, you will see. Yeah. Right. Cool. Moving on to the next one. A cylinder of a weight W is resting on a V groove as shown. Draw the free body diagram. All right. Very interesting, guys. Start off with the basic forces. What is the most basic force? The weight. Next, apart from the weight, there will be two more forces over here. One will be the normal force here, and the second will be the normal force over here. That's it. These are the two additional forces which will come. If I call this N1, let's say this will be N2. That's it. These are the only two forces. Everyone, till this point, absolutely clear? Now, if at all I know what the angle is, if at all I know what the angle is over here as well as here, I can resolve the forces very, very easily. So if this is theta, this is theta. What happens is, observe carefully now. Observe carefully. This is that incline right over here. This is that normal. So what you do is show one more dotted line over here. And we know that if this is theta, even this particular thing is theta. I will draw one vertical line over here. I draw one vertical line over here. Now tell me, guys, if this is theta, how much will this angle be? How much will this angle be? Because this is 90 degree. Obviously, won't it be 90 minus theta? If that is so, if this is 90 minus theta, can you think and tell me how much will this particular angle be? Because this is 90 degree, so it will be the complementary of that, which means it should be theta. Same way, again, I can see that this particular angle will be complementary of this. That means it will be 90 minus theta. Again, this is complementary of that. So basically, this will be theta. And again, I can say this is 90 minus theta and so on and so forth. So again, this particular thing will be 90 minus theta. And if I extend this line before over here, sorry, extend this particular line over here, you will again see that this particular angle will be theta. And again, this particular angle will be 90 minus theta. They go alternatively. They basically go alternatively. So usually whenever you have inclined plane problems, preferably divide it into 8 parts, and you will see if one of the angle is known, automatically every set of angle will be known by you. Either it will be theta or the complementary angle of it. Theta or 90 minus theta. This part is clear? Okay. Now this normal will have two components, like you can observe carefully. This normal will obviously have two components. One component will be over here and the other component will be over here. So if I call this as N1, the horizontal component will be N1, sorry, it will be N1 sine theta component because it is far from theta, and this is closer to theta. So it will be N1 cos theta component. Do you guys agree with it? So N1 sine and N1 cos. Same thing can be said for N2 also. Same thing can be said for N2 also. If you draw the free body diagram, split it up, etc., you will notice that this would be N2 sine theta and this would be nothing but N2 cos theta. This would be nothing but N2 cos theta. Got it? Now, why did we split the components? Because I want to keep things simple. Everything horizontal, everything vertical. I don't want angles. I don't want inclinations. I don't want inclined forces. Now that everything is in X or Y, I can say, if you just consider the X direction, what you will notice in the X direction, weight is not even there. It is virtually only in the vertical direction. This and this should cancel. So N1 sine theta will be balanced by N2 sine theta. Sine theta will cancel. So N1 will be equal to N2. N1 will be equal to N2. They will balance each other out. If you look in the Y direction, if you look in the Y direction, the weight is downwards. It will be balanced by this and this component, which means N1 cos theta plus N2 cos theta. N2 cos and N1 cos. But N1 and N2 are equal. So it will be 2 times of N1 cos theta is basically W. W is nothing but mg. So it will be 2 times cos theta multiplied by N1. Therefore, the normal will be mg divided by 2 and cos theta. Therefore, N1 and N2 both are equal. So it will be nothing but mg divided by 2 sec theta. Is that absolutely clear, everyone? How we found this out? Yes. So this is how you solve questions. This is how you solve questions involving free body diagram. Cool. Sir, W is wrong. What is W is wrong? Why? Weight will be mg. What else? Sumesh, nothing wrong, bacha. It is not sine theta, N2 sine theta. It is both are cos theta only. This diagram is same as this. It will be N1 cos theta and N2 cos theta. So N1 cos theta plus N2 cos theta will be 2 times of N1 cos theta because N1 and N2 both are equal from here. So from this 2 times cos theta into N1, I can write it down. Weight is always the mass of this, okay, into G. Here they have already given W. So if you don't want, you can also write it as W sec theta divided by 2 also. It's one and the same thing. It's one and the same thing. Is that clear till this point? Sumesh, Pakka, check this out. Nothing wrong over here. Now, going to the next question. A block of mass m is attached with two strings as shown. Draw the free body diagram of the block. Draw the free body diagram as a of the block. Yes, we'll be taking a break after some time. No, no, no. That is fine. See, this was theta. This was theta. This was theta. So hence this is theta. If this is theta, this is 90 minus theta, this is theta, this is 90 minus theta. Normal is here. So this is N1 cos, this is N1 sine. Cos is always closer. C for close. This is basically far away component. If you give this as the angle of theta, then it will be completely different. Then this will be cos, this will be sine. That's the trick. That's the trick which you need to be very careful about. Okay, a lot of times many students make this mistake: when to take cos, when to take sine. Cos is closer, C for close, C for cos. Sine, you committed a sin by going far. Okay, so I can see that this particular angle is theta. So if I draw a line parallel like this also, two parallel lines intercept, this angle will be equal to this angle over here. And that is how I wrote this as theta. Okay, clear? Sumesh, see where you went wrong. All right. No, Sumesh, it is not N2 sine theta, it is cos theta only. Even for N2, you will notice this angle will be theta, just like this one. This was theta over here. The same thing, diagram, you write it like this. It will be N2 cos theta and this will be N2 sin theta. Okay. So please redo it. I think you are making that silly mistake again and again. Okay. I think you are thinking this is theta. No, this is not theta. This is theta. Why is this theta? You can again redraw the same thing for N2. It will be exactly mirror image of this. Yes. All right. You're making that silly mistake. Be careful. Now, for this particular problem, there is a block held by two strings. What are the forces? One will be the weight. Mass is m. So weight will be mg. This string tension, this tension will pull this block. If you draw the free body diagram of the string, tension will be here. But the block's free body diagram will be where the tension pulls the block by some tension T1 here. There is another string here. This string pulls this block with another tension T2. I do not like forces at an angle. I do not like forces at an angle. So what will I do? I'll split the forces. Closer is cos, so this will be T2 cos theta. Far away is sine, so this will be T2 sine theta. That's it. I don't have to split any of these. Now, if I write anything in the, let's say, y direction, I'll start with the y direction first. It will be easier. In the y direction, mg force will be balanced by the T2 sine theta force. Therefore, T2 will be mg divided by sine theta. I'll leave it over there. Okay, this is T2. I found one of the forces already, tension 2. If I see in the x direction, left side it is T1 balanced by basically T2 cos theta. But T1 is nothing but mg by sine theta. So therefore, I will say T2 will be nothing but mg by sine theta cos theta. For those who are a little bit interested in trigonometry, can multiply and divide by 2. So it will become 2 sine theta cos theta, which is sine 2 theta. So it will become 2 mg divided by sine 2 theta. That is the value of T2. T1, is this T2? I think, did I write something? Oh, sorry guys, I did a blunder over here. I had to substitute the value of T2. I substituted the value of T1. My bad. So sorry. So sorry. I had to substitute the value of uh, T2 over here. I substituted it here by mistake. So T2 is nothing but mg by sine theta, and this is nothing but cos theta. So this will become mg cot theta. mg cot theta. That is nothing but T1. So T1 is mg cot and T2 is nothing but mg by sine theta. That's how you find the forces. Is that clear, everyone? So are you getting a hang of how to draw the free body diagram in most of the cases? Yeah. Actually, whatever problems we solved now are actually the questions of equilibrium till now. You will see that there will be problems where it is not in equilibrium as well. So equilibrium problems basically means they are either at rest or in uniform motion So if it is at rest, it is called as static equilibrium. Whereas if it is in uniform motion, basically meaning the velocity is constant but not zero, then it is said to be dynamic equilibrium. In either of the cases, whether it is static or dynamic, the acceleration will be zero. Hence, by Newton's law, the net force on it must be zero. So all the forces balance. So all forces basically balance out each other. So one way of writing it is, the net force in the x direction is zero, net force in the y direction is zero, net force in the z direction is zero, or you can alternatively say, you can alternatively say all the forces in the left side balance all the forces on the right side. You put all the forces on the left, all the forces on the right, and write it on both sides of the equation. Or all the forces going up balance all the forces going down. Or all the forces which are coming towards you balance all the forces which are going away from you. So either this or this, it's one and the same. So what we have been doing all this while, if you notice, what did we do? All the forces going up are being balanced by the forces going down. T2 sine up, mg down, so balanced. Same thing over here. All the forces going up, n1 cos and n2 cos, n2 cos and n1 cos up, and weight is going down. So they are balanced. So that's why I put equal to. So you basically balance the forces, on LHS and RHS one way, or you can put all the forces on one side and assume upwards as positive, downwards as negative, right side as positive, left side as negative, and then write it with sign convention. Either ways, you get the same answer. Okay. So I think I'll be covering the, uh, you know, part two of current electricity PYQs tomorrow. And I think PYQ of NLM will give it a small gap so that you to practice few questions and come for that particular 2024 JEE PYQ session. Okay. Now there are just problems, problems, and problems. Shall we begin? Shall we begin? Curiosity, I'm so glad. And which standard are you in curiosity right now? An object is in equilibrium under four concurrent forces in the direction as shown in the figure. Find the magnitude of F1 and basically F2. There are four forces as shown over here, concurrent, okay, in equilibrium. And in equilibrium, what happens, guys? All the forces should cancel out each other in every single direction. So first of all, split the 4 Newton force in two directions, one here and one here. This will be 4 cos, because it is closer, 30, which means cos 30 is root 3 by 2, 2 cancels, so 2 root 3 Newton. And this will be 4 sine 30, which means sine 30 being half, it will become 2 Newton. Same way, this F2 will also have a component here. This will be F2 cos 30, which is F2 root 3 by 2. And there will be one component over here, which will be F2 sine 30, because it is away. That means it will be F2 divided by 2. Now let's start. Let's start by probably going in the x direction. Maybe it will be easier. Maybe in the x direction. In the x direction, if you notice carefully, there is only this force towards the left side, which is F2 root 3 by 2 towards the left side. Acting towards the right is 8 Newton and this 2 Newton. So 8 Newton and this 2 Newton acting towards the right side in the x axis. Nothing else is there. 8 plus 2 is basically 10. So guys, F2 will be 2 into 10 divided by root 3. That means 20 by root 3 Newton. That is the value of F2. Is that clear, everyone? Very good. Till this point, I hope it is absolutely clear. Till this point, yeah, great, great. Next, what about F1? What about F1? What will you do? How do you find F1, guys? Think about it. What will you have to do? What will you have to do? Yes, you have to balance the forces in y direction. Correct. So you'll have to balance the forces in the y direction. So in the y direction, observe what are the forces. One force is this 2 root 3 upwards. So 2 root 3 is upwards, which is the component of 4 Newton. Plus this F1 is also there. Nothing else is up. Down, you have this. Down, you have this, which is F2 divided by 2. So this was acting down. This was acting up. I just need to find F1. So substitute the value of F2 from here. So therefore, 2 root 3 plus F1 is F2. F2 is nothing but 20 by root 3, and this is by 2. So move it on this side. Therefore, F1 will be 2 root 3 minus 10 by root 3. Take LCM. So this will be root 3 below. Root 3 into root 3 will be 3 minus 10, right? So this will be nothing but 6. 6 minus 10 is 4, negative 4 by root 3 Newton. That will be the answer. Now, the value of F1 came out to be negative. What does this mean? What does this mean? The direction which is shown is wrong. Actually, F1 is not up, F1 is downwards. So that is the significance of this. That is the significance of this negative sign. So minus 4 by root 3 and 20 by root 3. Yes, that is the answer. Absolutely. Perfect. Let's move to the next question, my dear students, coming up on your screen, and here it is. One end of a string 0.5 meters long is fixed to a point and other end is fastened to a small object of weight 8 Newton. The object is pulled out aside by horizontal force F until 0.3 meters from the vertical through A. Find the magnitude of the tension in the string and the force. Okay. So basically some dimensions are given. The object is pulled aside by horizontal force until it is 0.3 meters. The end of the string, which is 0.5 meters long, this is actually supposed to be 0.5 meters long. Okay, you are pulling this till this point is 0.3 meters away from this side. It is 0.3 meters from the vertical through A. Okay. Now, question is find the tension in the string as well as that force. First of all, I think we should find how much is this particular angle. Let me find it out. I can say this is a right angle triangle. This is adjacent side. This is hypotenuse. So cos theta will be the most favorable ratio, which is 0.3 divided by 0.5, which is 3 by 5. This happens when theta is how much, guys? Theta is nothing but 53 degrees. So hence this theta is 53 degrees. We got that. Now it will be easier for me to solve. See, this tension will have one component here and one component here. The closer one is always cos. So this is T cos and this is nothing but T sine because it is far away. If you look at the y direction, in the vertical direction, T sine is up, is being balanced by downward force of 8 Newton. So T sine 53 is 8. Sine of 53 is nothing but 4 divided by 5. 4 cancels with 8 two times. So therefore, tension is nothing but 2 5s are 10 Newton. So we found the answer for T. We found the answer for the tension in the string. But another part is there where you have to find the force F also. So now you balance the forces in the x direction. T cos theta is basically F. T cos is here, F is there. Tension is basically 10. I have to write cos of 53 is basically F. What is cos 53? Cos 53 is basically 3 by 5. So 5 goes with 10 two times. So F is nothing but 2 3 is a 6. So 6 Newton. That is the answer. So 10 Newton and 6 Newton. 10 Newton and 6 Newton is the correct answer. Got it, my dear warriors? Cool. Everyone? Yeah. Yeah. Awesome. Awesome. Yep. Very good. Very good. Great. Great. No, previous question is fine, Tirupati. Nothing wrong in that. We got the correct answers only. Yeah. So this is 2 root 3. I think, oh, I took 10 root 3 here and 2 root 3 here. So sorry. I should have put this first and this first. Yeah. I should have put 20 by 2 is basically 10 by root 3 minus 2 root 3. LCM will be root 3. So this will be 10 minus 2 into 3. 6. 10 minus 6 is 4. So 4 by root 3. So direction wise, this is fine only. Nothing wrong. Yeah. Thank you for pointing it out. Yeah. Moving on to the next question. This is there in HC Varma. Wow. There is a block of certain mass which is pulled on a smooth table by string making an angle to the horizontal as shown. The acceleration is A. Find the force applied by the string and the table on the block. Already they have given the acceleration. Already they have given for the value of acceleration. We'll do this question and then we'll have a break. So the acceleration of the block is already given to be A. What are the different forces acting on that block? One will be its own weight, which is mg. Apart from that, there will be a normal force like this. Clearly mentioned smooth, meaning no friction. So there will be one additional force of tension over here. These are the only forces, nothing else apart from it. But I do not like that tension force because it is at an angle. It is at an angle. So I rather split it up here and here. The one which is close to theta will be t cos. The away will be t sine theta. Perfect. Now, if you write the equations in the x direction, it's only one force, but it is not balanced. This is in motion. This is the effect. So this force causes this acceleration. To think of it like this, the force in the x direction, the force in the x direction causes the mass to accelerate in the x direction. How much is that force in the x direction? Well, it is t cos theta. How much is that acceleration? It is itself a. That means the tension will be ma by cos theta, which means it is ma sec theta. That is the answer for the tension in the string. That is the question. What is the force applied by the string? That means the tension in the string. So that part we have found. Find the force applied by the string. That part we have done. Now, let's do for the y-axis because the table on the block normal is asked. A lot of you might think normal is mg, but no, it is not mg because there is a component of tension in the y direction which will play a spoil sport. So it will not let normal balance mg. So you will see in the vertical direction, it is the normal plus t sine theta minus mg is equal to mass into acceleration in the y direction. So acceleration in the y direction. What's the acceleration in the y direction? It's 0. So it is a big fat 0. Therefore, normal will be equal to take mg on the other side minus t sine of theta. But I already wrote the value of tension. It is nothing but ma divided by cos theta. And this is basically sine theta as it is. So it will become mg minus ma tan theta. If you want, you can write m common, g minus a tan theta. That's it. That is the value of the normal force. M into g minus a tan theta. Is that clear, everyone? Till this point? Yep. Very good. Very good. Awesome. Hi, Srividya. Karthik, this is an English channel. Yes, t sine theta plus n is equal to mg. Very good, Harborine. How sec theta? Please explain. Uh, Arlina, Jenny, I mean, just look at it in the x direction. There is only one component of tension, which is t cos theta, which is right over here. That is the only reason why it will accelerate in the horizontal direction. So the force is t cos mass into acceleration, which itself is a. Correct? So you had to find the value of tension. So bring that cos below. So 1 by cos is nothing but sec. 1 by sine is cosec. Cool? Marlena, Jenny, till this point, absolutely clear. You might have also seen this kind of question where there is just a single block of mass m and it is accelerating downwards, and find the acceleration. This kind of question, what you do is the forces acting are one normal force and the second one is basically mg. These are the only two forces acting on the block trying to slide down a smooth surface. Now, in order to find the acceleration or the normal, what I will do is I will split one of the forces. Which one will it be? Will it be normal or will it be mg? I feel it is better to split mg because already normal is perpendicular to A and I can take this as x, this as y. So automatically mg becomes the force at an angle. So what happens is if this particular angle is theta, you will notice that even this is theta. How am I so sure about it? Use my trick of 8. Whenever you have an inclined line and a perpendicular versus this horizontal and vertical, you know the angle of inclination is theta. Leave one part of that figure go to the next part, that will be theta. Leave one part, go to the next part. Leave one part, go to the next part. Every alternate will be theta. Use this trick. Use this trick, my dear warriors. So you can clearly see between the normal and the vertical. Between the normal and the vertical, it will be theta. That's how quickly you can analyze, or else you will get lost in that geometry. Mahesh Ramesh, this will be for 1.5 hours till 9 o'clock around. Once you do that, you know this component will be mg cos theta. This component will be mg sine theta. That's it. So down the incline, if you write down the incline, if you see down the incline, there is only one force and it is mg sine theta. So mg sine theta is that force. And how much is the acceleration? I do not know. So mm cancels. So g sine theta is a, or acceleration is basically g sine of theta. You got that. If you write the equations perpendicular to the normal, if you write equations perpendicular basically or normal, then there is normal, there is mg cos, and there is no acceleration in the y direction. It is only accelerating like this. There is nothing like that. So that is why into 0. Therefore, normal will be, take it on the other side. It will be mg cos of theta. That's how you find the normal. That's how you find the acceleration. Chemics, yes, you are very late. Yep. Okay. So we will solve. Okay, this was done. We'll solve the next questions right from here. All right. After a small break. All right. We'll take a small break and then we'll continue. All right, my dear warriors, my dear lions, I hope I'm audible, visible. Hi, Indian artist, SSCN. Hello, Siddharth. I'm starting my J preparation. I'll watch all your videos. Can I be able to clear J means? Definitely, Siddharth. Better late than never, and definitely you can uh, cover it up. Yes. Sakti, timetable for road series physics, very difficult to give because every week things change, but every week 1 to 2 chapters. And uh, uh, like I said, next 1 2 weeks we'll be completing circular motion, work power, energy, etc. Uh, and then we will be going on to magnetic effects of current. Then we will do center of mass collisions, uh, rotation, and then we'll be coming back to electromagnetic induction and all of that. Okay, that's what it is. Aditya, to become a teacher in Vedantu, yeah, first of all, clear JEE. Uh, Obviously, be from a great college, have the passion for teaching, have the passion for the subject, and whenever opportunities open up, it will come up on LinkedIn or on our page. Apply it. That's how you become a teacher. Yeah. Yes, crazy edits. I hope to complete it today. Uh, Hopefully. I wish I could do 2 hour classes, but unfortunately, it will not be possible because then if I do that, then our portion won't be completed on time. I want to do as much as possible in the little time that we have. That's why these marathons. Cool. Let's begin with the class. And here is the next question. Blocks of masses are placed side by side on a surface. A force is applied. Find the net force on the 2 kg block. Okay. Here, the choice of system plays a very, very important role, as you will see. If I want to find the force on the 2 kg block, well, net force on the 2 kg block, I think I can draw, or rather, I should draw only the free body diagram of 2 kg. This is your 2 kg block. There will be one weight acting on it downwards, of course, weight acting on it, which will be 2g, and there will be a normal force acting on it. 3 kg on 2 kg will apply a normal force like this. This 1 kg on the 2 kg will apply a force like this. These are the forces acting on the 2 kg block. As a result of all of this, this 2 kg block will be accelerating with some acceleration which I do not know. Now it is obvious that N1 and 2g will cancel because they will balance in the y direction. That's why N1 minus 2g will be 0, or rather N1 will be equal to 2g. So there is no net force in the y direction. But there is a net force in the x direction, which is causing that acceleration. So how much is that acceleration? I can find it out only by one thing, by taking this entire thing as a system. 3 plus 2 plus 1 will become 6 kg, and there is a force of 12 Newton. This system will accelerate. So force is mass into acceleration. Therefore, the acceleration is 2 meters per second square. Once I get the value of A, I will use it over here, and I will say that in the x direction, the net force is mass into acceleration. The net force in the x direction is mass into acceleration. Mass is 2, acceleration is 2, hence it is 4 Newton. So N2 is the larger force, N3 is the smaller force because N2 is in the direction of A, N3 is opposite to A. So N2 minus N3 is 4 Newton. So the answer is 4 Newton, which is correct, which is absolutely correct. Is that clear, my dear students? Yes, Nikhil. Time for questions. Similarly, if it was asked for 3 kg, you will do mass into acceleration. It will be 3 into 2, which is 6. If it was on 1 kg, 1 into 2, which is 2. So 2 Newton, 4 Newton, 6 Newton. That's the net forces on each of these blocks. Moving to the next question on your screen. Instead of blocks touching each other, these are blocks pulled by each other using strings. So that means there is a role of tension over here. 3 blocks connected with each other, light strings, that means ideal smooth surface. You apply 10 Newton, then find the tension T1. Again, the logic is, if you want to find T1, either find or draw the FBD of 2 kg or 3 kg. If I draw the free body of 3 kg, I will have T1 and T2, but T2 is not known. But if I draw the free body of 2 kg, I will only get T1 as an unknown, which is more practical to solve the problem. So I will solve the problem for 2 kg, but unfortunately I do not know the acceleration. No issues. Take the entire thing, take the entire thing only as a system, which is 2 plus 3 plus 5, which is then 10 kg. And the force on it, and the force on it is how much? 10 Newton. So there will be some acceleration. So force is mass into acceleration. Mass is 10. Acceleration will naturally come out as 1 meter per second square. Once I get that, I will just consider the 2 kg block. I will just consider the 2 kg block. I will show that it has an acceleration of 1 meter per second square. Apart from that, there is a force of 10 Newton on this side and T1 tension on the other side. So the net force is mass into acceleration. Net force will be 10 minus T1 or T1 minus 10. Obviously, since it is going towards the left side, this should be larger than this. Leftward will be more to accelerate it. So the unbalance is towards the left side. So it should be 10 minus T1, not the other way around, is equal to mass into acceleration. Therefore, T1 will be 10 minus 2. Therefore, T1 will be 8 Newton force, which is the correct answer. Is that right? Option C for Captain Shreyas. Very good, Nikhil Harborai. Most of you got it. Straightforward. Awesome. Moving on to the next question. A dynamometer, D, meaning a device which measures the force. How do you measure the force? Use a spring and let it elongate. Based on the elongation, K into X is the force. Very simple. So spring can act like a device to measure the force. If you know how much is the extension or the compression and the value of the spring constant, multiplying them, you will get the force inside the spring. Okay, so there are forces F, 20, 10, masses 6, 4 are applied on the masses. The dynamometer will read how much? Okay, let's see. I think we'll have to solve this problem individually because the spring might be extending. So if I consider the left side mass, which is how much? 6 kg. So this is 6 kg. There is a force of capital F here, and there is spring force. Spring force is there. So I'll put Fs over here. Okay, apply to the masses. And the question is, how much will it read? There might be some amount of acceleration also involved over here. Let's say I call it A1. Similarly, if you consider the right side one, there is one force over here, small f, and there is another force over here, which is the same as the spring force, which is Fs, and there might be some amount of acceleration A2 over here. There might be some amount of acceleration A2 over here. Is this fine? Till this point? Clear absolutely? Great. Now, the question is, what is the reading of the dynamometer? Forces are given, masses are given, the dynamometer is attached, and the forces are applied. Here, if I solve it also, I have many unknowns. Spring force, A1 and A2. Spring force, A1 and A2. There are multiple unknowns over here. So there is something which we need to tackle even before this. Do you agree with it? I have only two systems, capital M and small m. Maximum I can get two equations, but the variables that I have, A1, A2 and Fs, they are three in number. So two equations, three variables doesn't seem solvable. So what do you do to solve this particular question? Is there something that we are missing? Is it something that we need to uh, figure out in this particular question? Thank you so much, Sri. Thank you so much. What will you do for solving this particular question? Think about it. So guys, if you write the equation for this, let's say what do you get? You will get F minus Fs is equal to mass, which is 6, into the acceleration. Okay, that's what you will get. If you write the equation for this, by the way, over here, one small thing, this F, capital F is basically 20. For the other mass, for the other mass, 10 minus Fs, 10 minus small f is 10, okay, 10 minus Fs is smaller mass, which is 4 multiplied by A2. Interesting. I want to find Fs. I don't want A1 and A2. Maybe something else I need to do over here. How about adding both of them? How about basically adding both of them, right? So what we can do is basically we can just write it over here. We just add them both over here. So this will be 20 plus 10, which is basically 30, minus 2Fs is basically 6, what do you say, A1 plus 4 times of A2. 6A1 plus 4 times of A2. Now, what is the value of A1 and A2 over here? Is it given to us? Is it given to us? No. If it is not given to us, we will not be able to solve that particular problem. Will not be able to solve that particular problem. Do you understand that? Yes. If A1 and A2 is not given to us, then without it, can we solve that particular question? Think about it. No, right? Getting my point? Yep. Everybody till this point clear? Yep. We do not know what the values of these accelerations are, because these accelerations will continuously be changing at every given instant, because the spring force itself will be changing. So unless I know A1 and A2, we won't be able to solve the question. Okay, so I think there is something which is missing in this particular question, which is specifically A1 and A2 values. If that was given to me, definitely I would be able to solve this. Is that clear till this point? Everybody will with me? Cool. It will depend. At different times, these accelerations will be different. So these A1 and A2 are not known. Only when I know this, I can find Fs. So I think the diagram was incomplete. Without the diagram, we'll not be able to solve it. Let's go to the next one. A system is shown in the figure. All surfaces are smooth. By the way, just one simple thing. For example, if they give you, for example, they had given to you what the accelerations are. Let's say they had told, listen, this acceleration is, I don't know, chumma, I'm saying 1 meter per second square, or let's say it is 2 meters per second square. And let's say they tell you, listen, this particular acceleration is 1 meter per second square. Then you would be able to solve if it was given to you. So then you would be like, this is 6 into 2 plus 4 into 1. So 6 2s are 12. 12 plus 4 is basically 16. So basically take 16 over here. So 30 minus 16 is 2 times of Fs. So 30 minus 16 is basically 14 is 2 times of Fs. So Fs will be then 7 Newton. Okay. Right now, we cannot solve the problem because it is not at all given to me. It is not at all given to me. Else, this is how you will solve it. Perfect. Moving on to the next question coming up on your screen. In order to solve this particular question, I will make you solve another question coming up over here. This is another standard question which everybody must know. There is a mass suspended here. There is a string. There is a pulley. That pulley is being held over here by the roof, and another mass is suspended over here. This is mass 1. This is mass number 2. Let's say mass 2 is more. So what will happen? The system will start going up and down. Heavier will go up. Sorry, heavier will go down, and the lighter one will go up. If it is going up with A, this will come down with the same acceleration. I want to find the acceleration and the tension in the row. So how do I do that question? So let's solve this. I want to find the acceleration tension in the row. So what I will do, if I draw the free body diagram of this particular mass, there will be one tension here, there will be one mass over here, m2g here and tension over here. Is that right? That is what it is. Yeah. Sir, if we can find the value of A2, sir, then we can find the spring force and we can complete the question, sir. Yes. If either A2 or A1 were given, we would be able to solve the question. But if it is not given, we cannot solve the question. That's how it is. Yeah. Okay. Now, these are the only forces acting on this particular mass M2. Similarly, on this particular mass, there is one force which is M1G and the other force which is basically T. Why T? Because the same string is connected to the masses. Correct? Now, if you write any equation for M1, how will it look? Observe. Mass number 1 is going up. So the net force should be up. So tension should be positive, M1G will be negative. Tension is helping the motion, M1G is against the motion. So this is the net force is equal to mass into acceleration. Similarly, if you write any equation for mass number 2, how will that look? Well, mass number 2 is going down. So downward forces will be positive, upward forces will be negative, because it is that force which is helping the acceleration which will be positive. So M2G will be positive, tension will be against it. So that will be mass. This was M1, this is M2, mass into acceleration. What is the next simple step that you will have to do? Obviously, add both of them. So when you add both these equations, T and T will cancel and you will be left with M2G minus M1G is equal to M1A plus M2A. A is common over here and I will get M1 plus M2. And over here, G is common, so I will get M2 minus M1. So naturally, the acceleration value will be G into M2 minus M1, the whole thing divided by M1 plus M2. So that part is done. So I have found the acceleration of that mass, either going up or down. That's the magnitude of it. Heavier will go down, lighter one will go up. Cool till this point? Clear? Yeah. Tension is acting upwards, Nikhil. Yes. In spite of that, you will take it as negative. Why? Because it is against the acceleration. So all that you need to do is whenever you consider individual bodies, all the forces in the direction of acceleration which help it will be positive forces, which are against it will be negative forces. So check the direction of acceleration to decide whether it is positive or negative. That's why here tension was positive for this mass, but for this mass, tension was negative. That's something which you should learn from this problem. Cool? Clear? Shall we go ahead? Next part is basically to find the tension. How do I find the tension in this particular problem? Well, let's see. We can use any of these equations to find the value of tension. Let's say I use this particular equation. T minus M1G is equal to M1A. T minus M1G is equal to M1A. So therefore, tension will be equal to M1G plus M1 into A. But wait a minute, A, I just found it out right over here. So it was nothing but G into M2 minus M1, the whole thing upon M1 plus M2. So G is basically common. G is basically common everywhere. So let me take G common everywhere. And what I'm left with, in fact, even M1 is also common. You can see M1 is also common. So 1 plus M2 minus M1 upon M1 plus M2. Okay, so we have to take LCM basically. It will be M1 plus M2 below. Right? Is that right? Yeah. So we'll have M1 plus M2 plus M2 minus M1 on the top over here. M1 will cancel. It will become basically 2 times of M2. The whole thing upon M1 plus M2. The outside thing always remain as it is, which is GM1. So it will become 2 M1 M2G the whole thing divided by m1 plus m2. So that is the value of tension. That is the value of tension. I'm very good, Kathir. Yep. If they are stationary, then tension will be equal to mg, and then there is no fun in it. Tension is mg, tension is mg. So somebody is holding it. That's all. That's the value of tension. Simple, understood? Okay. Now there could be an additional level question in this, and they might ask you, what is the reaction on the pulley? What is the reaction on pulley by the roof? So in such case, if you draw the free body diagram of that particular pulley mass system which is supported from the roof, the forces on the pulley will look like this. There will be tension on this side of the string like this. The string is wrapped around it. The string is pulling that pulley down like this. And another tension here, assuming a light pulley, no weight, so you can ignore it, else the weight will also come. And the roof will be supporting it with a normal reaction. That's it. That's the complete free body diagram. And this entire system is basically at rest. So all the forces must balance each other. Therefore, normal will be T plus T, which means 2T. Wait a minute. I just figured out the value of tension. It is this whole value. Hence, it will be 2 into 2 times M1 M2 G, whole thing divided by M1 plus M2. Hence, it will be 4 times M1 M2 into G, the upon M1 plus M2. That's the reaction by the roof on the pulley. Yep. What is the direction of tension if they were stationary? Depends on which part of the system are you considering. Yep. If you're considering, doesn't matter whether it is stationary or not. Imagine if this mass was at rest, this is the string. If you're holding it, tension will still always be away from the string element, whichever part you consider. If you show this part of the system, on this, the tension will be here, always away from the string, away from the string. That's how the tension will act. Is that clear? Whether stationary or at rest or in motion, always away from the element that you have considered. Is that clear? Yep. Awesome. Awesome. Now here, what is the catch is that we have assumed that this particular pulley is nothing but light. If it was not light, then there will be one additional weight term which would have come plus W, plus W, plus W, etc. That's the additional term which would have come had it not been a light pulley. Click it. It is fine, bacha. Nothing is wrong. Moving on to the next question coming up on your screen. In the system shown figure, all surfaces are smooth. Find the tension in the string. All right. Instead of one hanging this way and one hanging this way, one going up, one going down, it's going like this. You leave the system, one goes down, it pulls the string pulls this block on the top, the system goes like this. So the question is, what is the tension in that string? All right. So let's solve. First of all, what are the forces acting on each of these blocks? 4 kg will have its own weight, so it will be 4g. Another thing will be the tension in the string over here, and it is accelerating downwards. So I'll show the effect also. Next, for this 2 kg block, its own weight 2g is here. There will be one normal force here, and there is only one singular tension here. There is no friction as such, but it is also having the same acceleration, because as much as this goes down, this goes towards the right. So let's start writing down the equations. For the 2 kg block, the tension is the only force, singular, which causes the mass to accelerate by a. So basically T is equal to 2a in the x direction. If you look at this block, the acceleration is down. So 4g helps in the acceleration. Tension acts against it. So therefore, 4g minus tension is the mass multiplied by acceleration. This is the net force. This is mass. This is acceleration. So what is T? We just figured it out right over here. It is basically 2a. So this will become 4a over here. So 4g will become 2a plus 4a, which is 6a. So g is basically 10, guys. So 6 multiplied by a. So therefore a will be divided by 2. This will become 3. Divided by 2. This will become 2. So 20 by 3 meters per second square, but that is not what is asked. What is asked is the tension. So tension will be 2 multiplied by acceleration, which is 20 by 3. So it will be 40 by 3 Newton. That's the value of the tension. Is that okay, everyone? Cool. So the value of the tension is 40 by 3. Acceleration was 20 by 3 meters per second square. So always start with free body diagram, identify the bodies, never ever forget to show the effects, which is the acceleration, split the forces if required, write as many equations as you need, and then solve the problem. Yeah. Okay. Harish, target is to complete at least 70 to 80% by, September to October. That is the target. Moving on to the next question on your screen. Here it is. In the system, the acceleration of 1 kg mass and the tension in the string connecting A and B is. You know what? This diagram looks as if that C is 3 kg. Okay. You take this string. There is a pulley over here, no doubt. Over here. Combine this 3 and 1 kg into single mass, it will just become 4 kg mass. And this system we have already seen. What is the acceleration? What is the acceleration? This 4 kg will go down, this 3 kg will basically go up. We have solved this problem. This acceleration was g into m2 minus m1. That means bigger mass minus smaller mass upon bigger mass plus the smaller mass, which is basically 3. So 4 minus 3 is 1, 4 plus 3 is 7. So it will be basically g by 7. So acceleration is g by 7. I can see g by 7 only in one option. Without even looking at the other thing, I can directly mark option C. But say for example, there were 2 or 3 options with g by 7. Then it can be confusing. You cannot select anything. You cannot blacklist anything. So what you will do in that case? Well, the next part is string connecting A and B. This is that string. Just consider the free body diagram of 1 kg. There is a tension over here. Why the tension is here? Because I am showing this block's FBD. So understand, this plus the block is my system. If you see this string, away from the string will be up, towards the string will be down. Tension always acts away from the string. So that's why tension is here. Some people think tension is below. No, tension always pulls that element. So I'm considering that knot which is there on that block. So if you consider that, tension is here. Obviously, I can't draw the free body diagram of the string. It's useless. The weight is 1g down, and the acceleration, of course, is upwards. How much is the acceleration? G by 7. Oh, sorry, not upwards, my bad, downwards. It is basically G by 7. If it is accelerating downwards, anything down will be positive. So 1g minus t is equal to mass into acceleration. So therefore, tension will be 1g minus g by 7. Basically, g minus g by 7 is 6g by 7. That's the value of the tension. 6g by 7 is there in option C itself. Exactly what we were expecting it to be. Cool. Is that clear? Understood? Very nice. Very nice, my dear students. Let's move to the next question coming up on your screen. Here is the next question. The block shown in the figure has a mass m and descends down with some acceleration. The mass of the string below the point A is m. Find the tension of the string at the point A at the lower end. Okay, observe. The block is as shown in the figure, that has capital mass and it goes down with an acceleration. The mass of the string below the point A, that means they are saying this much mass is basically small m. Find the tension in the string. Basically, they are asking you in this part of the string, what is the tension? Guys, this entire thing is clearly mentioned that it is going down with some acceleration A. So just consider this particular part as my system and let me draw the free body diagram. Already tension is there. Tension I have shown. The only extra thing that will come is the weight, but this will be the total weight. So it will be m plus small m into G. M plus small m into G. Is that correct? Now, since it is going down, downward forces will be positive, upward will be negative. So hence I will say m plus m into G minus T is equal to the entire thing is accelerating with the same acceleration. So therefore, tension, take it on the other side, bring this over here. It will be m plus m into G minus m plus m into A. So it will be m plus m common and I will have G minus A. So that's the value of the tension, m plus m into G minus A. Is that clear? Tony Stark, please solve questions. DPP, number one, your textbook. Number three, your problem. DPP, either your coaching gives, I am giving. You should have a lot of DPPs. DPPs are a must. And if you see how toppers study is class duration might be 3 hours, but their practice duration is at least 3 hours. So that's when you get a really good percentile. So if you study a chapter, watch lectures, PYQ, whatever, you should have minimum 1:1 ratio. Ideally, you should go 1:2. If you watch for 1 hour, you should practice for 2 hours. Not reading theory or making notes. I'm saying practicing questions, bare minimum. Then that will be the right amount of study that you will do. And always go from easy level to moderate, then above moderate, then J mains questions, then you extend your level to J mains and beyond, and then solve previous year J advanced question. So that is a step-by-step approach. Okay, so Tony sir, that means you need to solve more J mains PYQs. Then you need to solve those questions which are between mains and advanced. Then slowly go to very good advanced questions before you pick up previous year advanced questions. Directly, if you pick up a very good J advanced question, it will always be tough. So pick up something in between, the tough mains questions or the easy advanced questions, that middle questions. Then level up. In that advanced also there are different categories. It is not like every advanced question is very difficult. Slowly push it up. Slowly. All right, so this is done. All right, perfect. So let's also see the concept of spring balance and weighing machine before we go ahead. You will see many questions like this. See guys, um, there was this famous puzzle. Um, spring balance measures mass or does it measure weight? Everybody might have seen a spring balance. There are some markings on it. There is some needle maybe somewhere over here, which might go up and down. There is a hook. There is a point which you connect to the roof or hold it, and you attach whatever mass you want to measure over here. Is that right? This is your spring balance. What does it exactly measure? Similarly, if you take a weighing machine, you might have seen that there are markings on it and there might be a needle. You put a mass on that particular weighing machine. So this could be your oops, weighing machine, something like this, kept on the ground. You have kept a block over it. And then there is this another device where you have some mass over here and then another mass over here. And then you have these weights which you know, and you keep it over here. And then you compare it and you see whether the beam balance exactly stays horizontal or not. Test here. Let me tell you, the situation is very, very bad outside right now. Uh, I mean, if you talk about not just IITs, everywhere, everywhere because of recession, many students who have even graduated from IITs are not getting a job. It's not because there is any problem with IITs. Some people are claiming some stupid reasons also. No, it's because there is a recession going on right now, and this recession is going to continue maybe for some more time. Nobody can predict that. So, ideally, in such a scenario, if you can afford to do a post graduation, do it. So that way you can postpone joining your job unless you have responsibilities. So that way, 2 years you will get a degree and higher qualification. By that time, we hope that the recession will go away and then you can get a placement. Otherwise, if you want to get a job, then you need to really work it out. It is not so simple. You need to probably undergo some courses, some skill training, some particular certificate which might be needed in a particular company, and make contacts, be in touch with many people, do some more internships, and slowly get pre-placement offer. So that is what I would advise. If you can do a dual degree, then it is better. Yeah. All of them measure mass, says Nikhil. I do not agree with that. No, they do not measure mass. It's only the beam balance which measures the mass, whereas these two always measure the weight. They always end up measuring the weight. Only this is the one which measures the mass. You know why? Imagine you take a beam balance on moon. You will still need the same counterweights to balance it. If you stand on a beam balance, even on Jupiter, Moon, Saturn, anywhere, you will see the beam balance will be balanced only when the masses on this side and masses on this side are same. That means it is measuring mass. But a weighing machine or a spring balance will change its reading, because what it ends up measuring is indirectly the gravitational force which it experiences by the mass which is being hung or being kept on it. So on Earth, the moon, the gravity changes. So the gravitational force changes. So the weight changes. So the reading will be affected by G. Is that absolutely clear? Yeah, yeah. I said weight is mass in English language, but today is physics, Nikki. I know it is very misleading, right? Often. So in that English, not like that English which I'm talking right now, but day-to-day life, colloquial language, we say, hey, what's your weight? Nobody says in Newton. First of all, half the people who have not taken science may not even understand what is a Newton. So that is why we do not do that. Is that clear, Nikhil, Arora, and Tony? Awesome, awesome. So what happens is, for a spring balance, think of it as if there is a spring and there is a needle over here and there is that hook, right? And there is some mass which is attached. So what happens is, uh, this mass will experience some weight, which will be basically mg. There will be some tension. That tension will also be the spring force. The tension will also be the spring force. So what will happen is that mg will be equal to T, which will be equal to the spring force. So that will be the reading of the spring balance. That will be the reading of the spring balance. Now what happens is, for example, if the mass is example 6 kg, then your spring balance force, which will be 6g, it will be 60 Newton. But this is the force in the spring, but the reading shown will be basically 6 kg weight. The reading shown will be 6 kg weight, because the markings on that scale, the markings on the scale will be such that if it is showing 60, they will remove 10. They would have calibrated to show the reading on Earth. So, it will show 6 kg weight. Actually, it is measuring the force. You think internally there is 6 into 0, basically, sorry, 6 into 10, which is 60 Newton. So that's the force which it is indirectly measuring. If you take the same spring balance on the moon, the gravity is 1/6. So the reading shown will be 1/6. It will end up showing 1 kg. So this will probably go up and it will only show 1 kg. It will not show 6 kg. Is that clear, everyone? Okay, perfect. Now, same thing applies for weighing machine also, guys. So if you have a weighing machine and you have kept some mass on it, what does the weighing machine exactly measure? This mass will have its own weight, which is mg. There will be also a normal reaction by the weighing machine. So on the weighing machine, there will be a normal as a reaction. There will be a normal as a reaction if I consider this as my action. So the reading shown is always the normal force acting on it, which in this case is mg. The normal acting on the weighing machine from the top is the reading which it is going to show. So say for again example, if there is a person whose mass is example 7.5 kg, the reading shown will be 7.5 g, which is 75 newton, which is 7.5 kg weight. If the mass is 7.5 kg, it will show 7.5 kg weight. Actually, it is 75 newton force. If you stand somewhere else, the answer will be completely different. Okay, meaning on another planet. Is that clear, everyone, till this point? Awesome. So imagine this. If I give you this particular question, if you can solve it, I would be very, very happy. Imagine there is a spring balance over here. It's pretty much massless. Okay. And there is a pulley over here. And there is, 5, or let's say, yeah, let's take 5 kg. 5 kg mass over here. Again, there is a pulley over here. And now here also you have 5 kg mass over here. Can you tell me the reading shown in the spring balance? Can you tell me the reading shown in the spring balance, my dear students? Quickly think and tell me. Can you quickly think and tell me the reading shown in the spring balance? If we calibrate the spring balance to the moon's gravity, then we can find the mass in the moon correctly. Yes, Nikhil, correct. So the scale needs to be changed. So whatever markings are there, you need to rub it off and repaint it with the new spacing and new places where you will put those markings. Then it will show the correct reading. That is called as calibration. Correct. A lot of you might be saying 5 kg. Some of you might be saying 10 kg. Some of you might be saying 0. Yes, I was expecting that. 0 Newton. If you mark 0 Newton, very good. You guys are thinking like I wanted you to think, which is the wrong way. People think there is same force from both sides. Both the forces cancel and the answer should be 0. Guys, remember one thing. Spring balance never ever measures the net force. See, if you consider this spring over here, do you really think there is only one force, which is the weight? No, from the roof also there is a force. It should balance the weight. So it is W only, numerically. So net force on a spring is always 0. I mean, when you extend the spring, you will see that the forces will, cancel each other out. W from here, W from here. One is the supporting, other is the force which extends or compresses it. So don't think, if there are equal forces, they will cancel each other out. No, in fact, they are acting like a supporting and the other one is acting like a pulling or extending force. So think of this problem as if you're applying 5g Newton force here and 5g Newton force here. One is basically the support and the other one is used for the reading, basically by extension, by extending it. So guys, the answer is the reading will be nothing but 5g, which is 50 Newton, which is also 5 kg weight. 5 kg weight. That is the answer. It is not 100. Thank you, Sujan, Sundar. Thank you so much. Means a lot. Sir, is this chapter important in the weightage of JEE Mains? SRL Devesh, no, this is not at all an important chapter, weightage wise. Number two, the concept of these concept from these topics of this chapter is useful everywhere. That is why it indirectly carries weightage. Number two. Number three, I made a video why nobody should watch such stupid videos of which chapters to skip at this point of time. When you have time, see, when you watch it in November or October, it is justified. I will only make that video. But right now, you have time, so don't even look at weightages. I know many students look for it because, and many people will make such videos also because you will get views. If I make, I can also give you right now 10 chapters to study, and you will 100% get very good percentile, much more than 95. 10 chapters, more than enough. And everybody will start studying those chapters. But then you will be like, wait a minute, uh, now your plan will get automatically extended. Instead of completing 20 chapters in 4 months, now you'll be like, let me complete 10 chapters in 4 months. And you know how planning works. You plan for 10 chapters, but it will not happen. You will complete 6 chapters only. Then once the deadline comes, you'll be like, oh my God, I didn't do those 4 chapters. You will search for one more video where which topics are important, which is high weightage, which is low weightage. You will say something else. This is not important. That is not important. Again, you will skip few more chapters. So this process continues. You will lose confidence. You will not even do things as per plan, and you will end up skipping even more, and you will not get those desired percentiles. So that's why never bother about weightage, especially when you have time. Think as if you have to complete the entire syllabus. End of story. Now I have a very tricky question. If you guys answer this 100%, you will get 99 percentile and above. I will make this 15 kg. Can you now tell me the reading in the spring balance? If you give me the answer, 100% you will get 99 percentile in physics at least. You might be thinking, sir, now it is very simple. I'll take 5 and 15. I'll subtract the two. 10 kg. That is the answer. Isn't that so? Hmm? The problem is, it will no longer be at rest. This will go down. This will go up. This problem is like saying there is now a pulley which is here. There is a mass which is 15. There is another mass which is 5. This is going up. This is going down. So guys, now the reading shown over here will be the tension. So the reading which you want in this string here, anyways the spring is light, will be basically the tension in this particular string. That's all. So just find that tension in this string. How do you find the tension? I just gave you the formula. So the reading will be the tension. It will be 2 m1 m2 divided by m1 plus m2 into g. We just did it sometime back. Mass number 1, 5. Mass number 2, 15 divided by 5 plus 15 into g. Okay, so 2 into 15 5s are 75. 15 plus 5, 20 into g. 2 goes with 20, 10 times. So this will be 7.5 g, which is 75 Newton, or you can say 7.5 kg weight. It is neither 5 nor 15 nor their average nor their difference. It is something else only. It is 7.5 kg weight. That's how you solve the problem. So understand the concept. That's it. There was this another interesting question where there is a Pandu whose mass is 60 kg. He's he's standing is standing on a what happened? He's standing on a weighing machine. He's standing on a he's standing on a weighing machine, and this particular platform, this particular platform which is there, that itself is 40 kg example, and this person is holding a string which holds that platform like this. Question is, what is the reading? Question is, what is the reading shown? Very, very interesting question, guys, if you notice. Very, very interesting question. How do you solve even such a question, right? Such an interesting question. It's completely about how you show the free body diagram. Now, first of all, luckily, this platform is at rest. If the platform is moving, then another headache. Oh, let's take that headache then. Let's make this platform such that this person, as he pulls this platform, accelerates up with example 2 meters per second square. That will create even more headache. Okay. So let's think about whose FBD I will draw, whose FBD I will not. Pandu, weighing machine, the platform, all together are moving up. So how about considering the Pandu plus the platform entire thing as one system? 60 platform has a mass of 40, so it will be basically 100 kg. It will be basically how much? 100 kg. It is Pandu plus that machine plus that platform plus basically that platform. So that is 100 kg. So the mass will be 100 g downwards, and there will be another mass, sorry, another tension over here. See, Pandu is being pulled by the tension here, platform is being pulled by the tension here. So technically there are two tensions, T over here and T over here. And this whole thing is accelerating at 2 meters per second square. So definitely T plus T minus 100 g is equal to mass, which is 100 multiplied by acceleration. Therefore, 2T is equal to 200 plus 100 into G, which is basically 10. So that is 1000. 1000 plus 200 is 1200. So tension will be 600 Newton. So we got the tension in the rope. Till this point, is it clear? Absolutely. Till this point, is it clear? Absolutely. Very good. But that's not the end of the story. What we need to also do is we need to find the reading shown by the weighing machine. Weighing machine measures the normal acting on it. So let me see what is the free body diagram of only our amazing Pandu. Our amazing Pandu experiences these forces. One, he's pulling the rope down. So the rope will pull him up by the same force of tension. His own weight is there down, which is 60 g, and there will be a normal force by the weighing machine. And the result of them is the acceleration upwards of 2 meters per second square. So if I show these forces and now write the equations, tension and normal will be positive, 60 g will be negative. This is equal to mass times the acceleration. I want n, so n will be 60 into 2, 120. 60g on the other side as plus 60g minus the tension. So it will be 120 plus 60 into g is 600 minus tension, which is basically again 600. Yes. So 600, 600 cancels. What do I get? Normal as 120 newtons. 120 newtons, which is 12 kg weight. So the reading on the weighing machine will be 12 kg. Actual Pandu's mass is 60. Isn't it amazing? Isn't it amazing? Loved the type of question, guys. Clear how to solve these questions on weighing machine or spring balances? Give me a thumbs up, then we'll go ahead. Give me a thumbs up, then we will go ahead. Hi Nagireddy, Chelraja. Yes, whatever doubt you can ask quickly. Don't say sir doubt, just ask it. Okay, if it is relevant to the topic, I'll definitely answer. Great. So that was the concept of spring balance weighing machine versus beam balance. Beam balance, so anyways, measures mass. There was nothing great in that. Now let's come to this concept of pseudo force. Now, before going to pseudo force, we need to go to one more small thing, that is the frame of reference concept. How is A2? It was given in the question. It was given. The actual question only told that is pulling it such a way that the entire thing is going up. Okay. Yes. Now, there is this concept of different frames of reference. Remember, frame of reference is nothing but your observational point of view. So it is an imaginary thing with some coordinate system, and you basically imagine an observer like our Pandu over here who is sitting here, who makes all the observations. He also has a watch with him, and he observes maybe the Champa who is going here. This is our beautiful Champa going here. So this is the person being observed. This is our observer. This is our observer. So this is an imaginary concept. Now this observer, it's his wish or her wish to do whatever they want. They might be at rest, they might be flying up, they might be falling down, they might be accelerating, they might be moving with constant speed, they might be going in some weird curvy manner, they might be going in circular motion, they might be going in a parabolic motion. It's their wish. You can't decide what the observer does. The object under observation will do things as per the laws of physics. If Champa's wish is to walk towards this, she will walk. It's her wish. But she will follow all the laws of physics when those things are happening. Observer also has their own wish. So, depending on who the observer is, Newton's laws may be valid, may not be valid, meaning usually the forces acting on Champa will be like this, something is here, something is here. All these are the different forces acting on Champa. And as a result of this, maybe Champa has some acceleration. Maybe Champa has some acceleration. Maybe the acceleration is over here. That is the relative acceleration. That is the relative acceleration with respect to frame. So this is acceleration of the body relative to the frame. Relative to the frame. So normally you would say that all the forces, if you add them, what you should get is the mass of that Champa into acceleration of the Champa. This is what normally should happen, but it may not happen because it depends on this observer. So this is only true only if this is only true only if this is valid, only if this is something called as inertial frame, if it is an inertial frame. But if it is a non-inertial frame, you will see that this net force will not be equal to m into a. This is for a non-inertial frame. Non-inertial frame, meaning non-inertial observer. Now, what are these two kinds of observers, non-inertial and inertial? Basically, Newton's laws are not valid. Newton's laws of motion are invalid in such a non-inertial frame. Essentially, what I mean to say, all those frames of references, all those frames of references, which basically move, which basically move uniformly, which basically move uniformly, they are said to be inertial frames. They are said to be inertial frames of reference, or the observer is said to be inertial observer. Move uniformly means constant velocity, no acceleration. Basically, they have no acceleration. Examples of that: Earth. Earth is an approximately inertial frame, or a car on the Earth going at constant velocity. It's going on a straight road with the same speed. It's an inertial frame. Or a lift going up or down, up or down with constant speed. Whenever speed is constant, velocity is constant, straight line motion, it is moving uniformly, it is said to be an inertial frame of reference. But when it does not happen, like you are sitting in a car which is accelerating, a bus which is braking, a, a bike which is turning, direction is changing, or suddenly jerk is there, all these are non-inertial frames. So, a non-inertial frame, a non-inertial frame accelerates, accelerates, or retards, or you know, jerks. There is some jerk, or basically turns, because of which I would say it is accelerated. So it accelerates basically, and such a frame is then called as a non-inertial frame. Okay, there could be many examples, like you are braking, you are increasing speed, okay, you are turning on a road, etc. All these are basically examples of non-inertial observers. Is this point clear? Earth is moving, but it is changing the direction so slowly. It takes 1 year, so many thousands and lakhs of seconds to rotate by 360 degree. It is not in 1 second. It's not like Earth is doing a drift. Zoom! I'm turning. No, it takes 1 year. So that is why it is a slow moving, slowly turning object. That's why approximately it is an inertial frame. No, no, inertial frames are not scalar quantity. It's not physical quantity. So frame of reference is not even a physical quantity. It's a imaginary concept. Concept and physical quantity, two different things. And this concept, right, whether it is being accelerated or non-accelerated, decides whether it is inertial and non-inertial. In inertial frames of reference, Newton's laws are valid. In non-inertial frame, Newton's laws are not valid. I do not like it. How can I take no for an answer? Imagine you are an observer, you are accelerating on a bike, zoom, 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 you are accelerating, you are seeing some Champa over there. Then will you say, oh my god, Newton's laws I can't apply? Oh my god, sorry, Champa, I can't apply Newton's laws. Sorry. Champa will be like, hey, what a waste fellow, yeah, you are. Just because you are accelerating, you will not be able to apply Newton's laws on me. It will be very disappointing. It will be very embarrassing in front of Champa. So we want to make it valid. We want to make it valid even in our non-inertial frame. So what we do is we see what is the observer doing. Well, the observer in this case is, let's say, accelerating. The observer in this case is, let's say, accelerating with some value A. Remember, non-inertial frame means the person or that observer should accelerate. So this is a non-inertial observer. Non non-inertial observer. Let's say acceleration is here. What you do is, apart from your regular forces being added or subtracted, and you writing this as mass into acceleration, which right now is not equal to make it into equal to, you add one more force, which is called as the pseudo force, which is called as the pseudo force. This particular pseudo force, magnitude wise, is the mass of the object being observed, which is m, into the acceleration of the observer, meaning a. But if you look at it direction wise, it is negative m times of a. Negative m times of a. So if your observer is accelerating this way, the pseudo force on this Champa will be exactly opposite. So Fp will be opposite. So treat one more force and then solve the problem. It will be done. Just add one more force. If we take long time frames, is Earth inertial frame? No. For a very, very long time, it will not be an inertial one. Absolutely clear? Cool? Till this point? Now, I will tell you how, without the knowledge of pseudo force, you know, it will be very difficult to solve the problems in many cases. Like for example, just imagine mm, you are a non-inertial observer. Okay, you are a non-inertial observer and you are running with some acceleration a, and what you see is some object which is mass m, which is kept on the ground. You'll be like, what are the forces acting on the mass? One is its regular force, weight, so mg is there. Another is normal, that's it, no other thing. And this is at rest. This is basically at rest. So if there was an observer over here who is also at rest, this would be an inertial observer. This would be an inertial observer. He can apply Newton's laws of motion. He will say, hey, wait a minute, normal and mg balance each other. So mass into acceleration. So left hand side is 0, right hand side is also 0. So Newton's laws of motion are perfectly valid. No issues at all. But look at this observer. He is running. He's running. He's accelerating this way. He will find the box going the opposite way. He will be like, wait a minute. On the box, there is normal and mg. Why is the box accelerating? There is no reason at all. There is no reason at all why this box should accelerate behind for him. He will think which force is acting on it. He will spend his entire life, but he can't find this force because it does not exist only. So we introduce this false, fake, pseudo means false or fake force, and that false or fake force will be this way. Will be this way. You're like, oh, on paper only, this force is there, not really, is causing this mass to accelerate here with acceleration A. You're like, okay, now it is fine. In fact, this is the only force which you introduce which goes against your cause and effect order. Every time, because there is a force, that's why it accelerates. This is the first time you are seeing because it is accelerating, that's why you apply a force. That means this is not a real force. That means this is not a real force. Did you understand it? No, here we are not considering angular acceleration and all of that. We'll talk about rotational frame pseudo force, which is centrifugal in the circular motion chapter. Here we are talking about 1D motion objects, objects going in translatory motion, not in rotational motion. Not just that, there is one more interesting thing. So I will tell you, this was the cause in this case, which caused this effect. It has changed the causality. Not just that, this is the only force which does not follow Newton's third law, if you think about it carefully. Pseudo force is applied on the box. If I call this as the action and then I ask you, who is the reaction? Many people I have heard them say, sir, the reaction is on the Pandu, so the pseudo force is here. I held my head like this. How can you show pseudo force on Pandu? Action, reaction. Guys, no, not valid at all. You cannot show pseudo force on Pandu because, first of all, that force was not even there. So you cannot say Pandu applied the force. No, Pandu did not apply this pseudo force. It was just on paper. It's an imaginary thing just to make Newton's laws valid. So it does not follow the, Newton's third law. Yes, Janvi. Yes, Nitya, you can use it. In this video, the chapter won't be completed 100%. You can see the way things are going. As I think of completing a chapter, but I go with the flow and I see your responses and I see your understanding. I see how we are going with the chapter. And if it takes time, I take that time because I want that concept to be in your head. It's not about completing the syllabus, it's about uncovering the syllabus. A lot of teachers cover the syllabus, guys. That is very important. That is very wrong. I mean, a physics teacher or any teacher for that matter, covering the syllabus is important. But what is more important is uncovering the syllabus. So I hope you understand the difference and support your Captain Shreyas sir in this course. right? So just to repeat what I just said, usually if I push an object, that's the cause, that's the force, it accelerates. But for this Pandu, he was just running in this direction. You see that box going there. He's like, why is that box going there? Why is it accelerating? Then he thought, hmm, there must be a fake force. So he applied the force after looking at the acceleration. So it is against your natural order. Usually, force is the cause, acceleration is the effect. Here, because of the acceleration, you are forced to apply the force. Second thing, it does not follow Newton's third law. So, third law is not obeyed by pseudo force. P is silent. Don't call it P pseudo. I heard some people saying, "Sir, this P pseudo force is there." No, I mean, who is this P pseudo force? Guys, it is not P pseudo force. It is pseudo force, like psychology and pneumonia. P is silent. Okay, Arlena. Hello, Chinambani. Everyone clear? Shall we go ahead? Hmm, awesome. And because of this, you get the concept of effective gravity, which is also very interesting. We'll just do this and the problems on that. We'll have a part two of Newton's laws of motion and friction. So we'll do friction and constrained motion, block on block problems, angle of repose, etc. together in the second part. Let me complete this concept and the problems on this. Okay, right now. Imagine a lift at rest and versus a lift going up or down. Here the lift is at rest. Here the lift is either going up or down, but with velocity constant. In this case, the lift is going up with some acceleration. Here the lift is going down with some acceleration. Okay. Now, in this particular scenario, you can obviously see both the lifts, if you consider them as observers, they are nothing but inertial observers or inertial frames of reference. But if you consider these two frames where the lift accelerates up or down, 100%, they are nothing but non-inertial observers or frames of reference. Non-inertial observers. So here we'll need pseudo force, whereas here we won't. So imagine there is some object placed over here, somewhere here. Doesn't matter. And if you show the forces acting on it, the real forces are only mg, mg, here again mg, again mg. In this particular scenario, because it is inertial, no need of pseudo force, no other forces act. So what happens is, you will see that this particular object will definitely accelerate, will definitely accelerate, will definitely accelerate. And in either of the cases, you can directly say mg force is equal to our mass into acceleration. So acceleration is basically g. So this is basically our true gravity. That means if you leave something inside the lift, it will fall down with the acceleration due to gravity, which you would normally experience on Earth. That's why I'm saying true gravity, because it is not something different from g. I'm actually experiencing gravity. So if I stand inside the lift, I will experience my true weight inside the lift. But now in these situations, there will be an additional force, like you can guess. Pseudo force always acts, like I said over here also, always acts opposite to the observer's acceleration. So if the observer in this scenario is going up, the pseudo force, will be downward. In this case, acceleration down, so pseudo force is basically upward. Pseudo force is mass into acceleration. It is mass into acceleration. And as a net result, this mass will accelerate with some value. This mass will fall down with a different acceleration now. So if I write down the equations, how will it look like? In this case, mg and ma are helping each other. So ma plus mg is equal to m into a, whereas here, what will be ma equal to? It will be uh, mg minus, why minus? Because it is opposite, so minus ma. That's it. So here ma plus mg, because those two forces are in the same direction as acceleration. Here mg is in the direction of a, pseudo force is opposite, so minus ma. That's all. So from this, what do I get my acceleration as? I get the acceleration as cancels as g plus a, whereas here I get the acceleration as g minus a. Here acceleration is more, which is perceived. This is the effective acceleration which is perceived by you. If you are standing inside this lift, because the lift is going up, because of inertia, all the blood will go down. You will feel like going down because you want to maintain your state, whereas the lift is pushing you up. So you will feel more weight inside this lift. That's why G plus A. When the lift goes down, it feels as if somebody removed the floor beneath your foot. So as the floor falls, you will feel light. You will feel as if you are flying a little bit, as if you are losing some contact. So that's why the perceived gravity is G minus A. Now this concept can be used for solving many questions or for creating artificial gravity even on Earth. Just imagine this, guys. Imagine this. I want to make somebody feel as if they are on Jupiter, where the gravity is roughly 3 times as on Earth. So, what I will make them do, I'll be like, listen, I have designed a joyride, and this joyride will take you up with an acceleration of 2g. So, what happens to any person who is inside this particular lift? You will see that the perceived gravity, that the apparent gravity, which is g plus a, will be g plus 2g, because 2g is the acceleration, which will become 3g. So he will feel as if his apparent weight is 3 times the weight on Earth. He will feel as if he's heavy. So you can feel as if you are on Jupiter. Similarly, imagine somebody says, sir, can you make me feel as if I am in free space, sir? I want to make myself feel as if I am freely floating in space, sir. I can't become an astronaut, sir. Sir, can you make me feel like an astronaut? I'll be like, okay, fine. I'll do that for you. Very simple. I'll make you go inside a lift. I'll make you go inside a lift, and then the cable of that lift, I will cut it. I'll cut that cable inside that lift. So what will happen? That you are inside. Sorry, guys, I did this with you. Don't feel bad. Okay. And this lift will now fall down freely. It will be a free fall motion, acceleration g. So whatever perceived apparent acceleration will be there, it will be g minus a. So it will be g minus g, which is 0, which is like free space. So you will feel as if you are in free space. You are as if in free space. Isn't it amazing, guys? Also, imagine there is a problem with some lift, and this lift is going up with an acceleration of 4g, and somebody inside the lift has thrown this ball and it goes and hits over here with speed u, angle theta. If they mention that, listen, the width of the lift is w, can you find this w? I'll be like, yeah, why not? Guys, a lift going up, the apparent gravity, how much is the apparent gravity? Apparent gravity will be g plus a, so it will be g plus 4g, so it will be 5g. This looks like a projectile problem to me. This looks like a projectile problem to me, and this width looks like the range for me. So I'll do one thing. I'll use the range formula, which is u square sine 2 theta divided by 2 times the gravity. But this gravity will now be the apparent gravity. Here the range will be the width. u square is u square, sine 2 theta is sine 2 theta. I don't think 2g was there, sorry. Uh, G apparent will now become 5g. That's it. That is the correct answer. This is how you find the width. So any problem, you can now solve it by replacing that g with G apparent. If you could solve the problem on Earth, now you can solve the problem even in the lift. Even a complex problem like this. Imagine there is a lift and this lift is going down with 2 meters per second square. In that lift, there is a pulley, there is a mass here, there is a mass here. Inside that lift, I want to find what is this acceleration. No issues at all. Normally, I know the acceleration formula. It is m2 minus m1, m2 minus m1 upon m1 plus m2 into g. But now, g won't be g. It will be g minus a. So it will be basically 10 minus 2, which is basically 8. So hence it will be 8 times of m2 minus m1 divided by m1 plus m2. That's all. Understood, guys, how to solve these questions? Understood the concept of pseudo force and where to apply it, how to use it? Isn't it amazing? All right, let's solve some questions based on complete pseudo forces. A pendulum is hanging from the ceiling of a car which has some acceleration with respect to the road. Find the angle made by the string with the vertical. Okay, is there a place? I don't think. Okay, fine. See, I'll explain you. This trolley is accelerating with some value. Because of that, if you hang a stone via a thread, because of inertia, the stone will move back. It will make some angle. The question is, what angle will it make? So in that moving frame, obviously it will be a non-inertial frame. It will be non-inertial frame. If you sit inside the moving truck because it is accelerating. If you show the forces acting on the bob of the pendulum, on the stone or the object, the forces will be one tension, like you can see over here. There is one tension, weight, and because you are accelerating here, pseudo force will be behind. So that is the reason why you will see the pseudo force will be exactly behind. These are the real forces. This tension and this mg, they are the real forces. Now it is making some angle over here, which is basically theta. Now inside that moving trolley, won't you see this particular bob at rest? If it is at rest, that means all the forces must be balanced. So that is the reason why you will say tension which has a component here in the horizontal direction, which is T sine theta here, will be balanced by the pseudo force, whose value itself is ma naught. So that is your T sine theta. And you'll also say in the vertical direction, which has T cos theta upwards, will be balanced by a downward force mg. Once you see this, clearly you can divide both of them. If you divide both of them, T cancels. Sine theta by cos theta is ma naught by mg. Cancels. So a naught by g is basically tan theta. That means theta is tan inverse of a by g. So this is the angle made by the bob behind. Angle made by the bob behind, so that it stays at rest in that moving truck. Is that clear, everyone? Understood? Perfecto. Let me know, my dear warriors. Perfect. Moving to the next question. This is in Tattva. There is an inclined plane having some inclination. The lift is going down with a retardation, the time taken by the block to slide down the inclined plane. Okay, let's think. Because it is inside a lift, I know if I can solve that lift problem on Earth, I can solve it inside the lift. Just that wherever I see G, I'll replace it with G plus or minus A. That's all. Okay. So there is an inclined plane like so. There is an object over here. It has to cover this distance in basically time t. It starts from rest. The length of this plane is L. Obviously, the downward acceleration we already know. How much is that downward acceleration, guys? I had calculated that. Remember, it is g sine theta. It is g sine theta. But this is on Earth. This is on Earth. Oh, okay. Keep that in mind. No issues. For this much displacement, using S is ut plus half at square. S is ut plus half at square. S is L, U is 0. Acceleration, it won't be g now. This is on Earth, remember. It will be g plus or minus a. So what will solve it for g? Later on we'll substitute g into t square. Rearrange 2l by g is equal to t square. Therefore, that means t is root of 2l divided by g. I think, yes, till now everything is fine. Oh, sorry, acceleration was g sine theta, my bad. I think I missed that sine theta over here. Sine theta and sine theta. Yeah, perfect. Now it is okay. Now this is not the end of the problem because I have to replace that g with something else. Remember, whatever I found is on Earth, not inside that lift. So see what that lift is doing. What is that lift doing? That lift is going down with retardation. That means the speed was more, then became less, then became less. So where is it accelerating? Oh my God. You know what? It is actually accelerating upwards. It is actually accelerating upwards. How many of you figured this out? It is actually accelerating upwards. So strictly speaking, that G apparent is G plus A. Whenever it is up, positive. Whenever it is down, it is negative. That's how I remember it. So replace this G with G apparent. That's all. So the actual time taken will be root of 2L. Instead of G, you will put G plus A and then you will put sine theta. That's it. That's the end story. And hence the answer is basically option number D. Hence the answer is option number D. Many people will make a silly mistake and put G minus A. Option D. Correct. That's the correct one. What a brilliant, brilliant question. So that was the end of part one. I think so. Yeah, friction and everything else we'll be doing it later on, not today. I have hopefully kept some homework questions somewhere. Maybe somewhere. Yeah, I kept an homework question right over here. Try to solve this homework question and answer it in the comments. I want the answer in the comments, and then we'll start with part two in the days to come. Okay, we'll try to complete it this week only. Okay, and as far as possible. This is your homework question. Okay, answer will be there in the PDF later on. Cool. Yes, Priya, because of retardation, that's why the acceleration was opposite to the velocity. Correct. You can think of it like that. Awesome. So, see you in the comments with the answer. Do not forget to like the session because that way you can mark your attendance and YouTube understands that you are interested in JEE. It will keep you away from all the distractions. And of course, subscribe or else you will miss my future classes. So stay subscribed on the number one JEE English channel in the country. Thank you so much. This was Captain Shreyas. Bye bye. Good night. Have a great time. Have your dinner and also attend the next classes. 9 o'clock PYQ classes, 5, 6 o'clock ROAR classes. Okay. Be regular. Thank you. Bye bye. Take care.